Great, some more. Anything else anyone wants to say?
Our basic Indian education system is more academic driven.
Yeah.
So how is Agastya trying to change it?
Yeah. So Agastya, as you saw in the campus, he said it's mostly academic in India. How is Agastya trying to change it? One is by introducing hands-on experiential learning, so that it's related to something physical, something in real life. You know, if you talk to a lot of students, even college students, they'll tell you, I don't know why I'm studying this. No, I did calculus in school. I don't know why I did it. In the sense, the teacher never explained how this connects to anything that I see in my life. Right? So one is hands-on experiential, showing the connection to real life. The third is our mission is to spark curiosity. So we like to do things that make students curious. Hey, why did this happen? What does this mean? To create surprise. See, create your ability to be surprised. That's very important. Most of us don't get surprised. But to have that ability to be surprised. So we try and create that. And the creativity is the making, the doing, the observing, the questioning. So that's what we're doing. At scale, we're reaching 5 million children every year. 24 states in India. So we have a long way to go. I'm not saying we'll address all the, but basically to shift from what to think to how to think. From what to learn to how to learn. That's what we do. Yes, ma'am. Why is Agastya? Classes 6 to 10. That's how we started. And partly why we did that was the people I surrounded myself with in the early years, they were all scientists, mostly, or scientific leaders. And they had, obviously the exposure was more to higher education. At best, what they could do was middle school. They couldn't go below that. There's no connection to primary education. So we ended up with a strong science orientation, middle school. But now, we are also doing grade 1 to 5. We're doing grade 1 to 5. It's growing, but it's not there yet. Hi, Vijay. Okay, so we can start.
Thank you, Ramji. Good morning and a very, very warm welcome. We are looking forward to a very exciting set of weeks here at the institute best known for science in India. We won't take much time, we will start right away. All our guests are here, participants are here. I will invite Haripriya to come over and start it off with a prayer song. I request the audience to stand, please. Thank you.
व्याख्या प्रकटित परब्रह्मतत्त्वं युवां वसिष्ठन्ते वसदृषिगणैरावृतं ब्रह्मनराय आचार्येन्द्रं कर्कलित चिन्मुद्रमानन्दमूर्तिं स्वात्मा रामं मुदितवदनं दक्षिणामूर्तमीडे सहना भवतु सहनो भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः। ॐ शान्ति शान्ति शान्तिः। ॐ शान्ति शान्ति शान्तिः।
Kunika, Suhani, can you just hand over the bouquet to Haripriya for the lovely prayer song? I would just invite our guests over to the stage. Professor Anand Suresh, please come over. Dr. Vijay Raghavan, our Principal Scientific Advisor. Shri Gopal Krishnan, Deputy Commissioner from Hyderabad of JNV. Shri Ramji Raghavan, Founder, Chairman of Agastya International Foundation. Welcome, sirs. We are indeed honored to have your presence. We will set the tone of this whole program, and for that, I invite Shri Ramji Raghavan to take over and invite the other guests for their address. Thank you, Ramji sir.
Thank you, Kumar. My profound thanks to all the people on the dais who made time to come. You know, Vijay came to our campus a few years ago, and when he said, maybe Agastya should get involved in nurturing highly able, talented kids. And that was really the catalyst that got us working on this program. So it may not have been a big thing for him, because he just invested a day coming and going. But for us, it made a big difference. So please give him a hand. Anand Suresh was introduced to Agastya by Dr. Atre, and he's been a great friend, supporter, originator of new ideas for the foundation. And he's a busy man. He's the dean of a big department here at the Institute, and he still finds it worth his time to invest in meeting people like yourselves. So let's give him a hand. And we've had a long association with the Navodaya schools. Ganu always believed that that's where a lot of the children were already pre-screened, and that would save us, Agastya, a lot of work in terms of identifying children from the vast, population of India, highly able children. And so want to thank you and your institution for really supporting us. And with that, I've already had some interactions with you kids, so there's nothing new for me to add, other than to say, you're the future of this country, and not just this country, the world. If we want the world to be a better place, then it really depends on all of us. But you being the future and the kind of age group that's full of energy, enthusiasm, think about your lives, whatever you choose to do, and say, I want to make a difference, and try and make it happen. Thank you.
Kushal, can you just come over and hand over a bouquet to Sri Ramji? Thank you, Ram, for addressing the children.
Thank you.
Thank you very much. I would invite Dr. Vijay Raghavan to address our future talent.
Thank you very much, and thank you all, Ramji and other colleagues from the Agastya Foundation, Anand Suresh and others from the Indian Institute of Science for this program and for having me here. It's a great pleasure to be here. I mean, that goes without saying. But I must say that, it's really, I'm trying to put myself in your shoes to see what kind of excitement and opportunities visiting a place even for a few weeks, a place like the Indian Institute of Science opens up. The excitement of what we can do opens up in a place like this. When you come in here, you see the beautiful campus and you see students going around, you have chances to go to laboratories and see what they're doing. And quite often, you will not know or understand the details of what is happening. But the most interesting part is you will see that people have the freedom and luxury, I should say, and all the resources to pursue their curiosity and answer questions. So why is this important to talk? If you look at the world today, you will see many people will tell you what problems the world has. And those problems are many. Problems of rising global temperatures, the challenges of sustainable development, the challenges of our biodiversity, and so on. And to you, young students, the statement of problems constantly is worrisome. What about myself? What about my life? What can I do? And that is where I think a place like this opens up opportunities. The reason for that is, this is the kind of place and these are the kinds of programs which let you explore what you love, what you want to do, and at the same time have a transformative impact. We can look at the impact of science and technology and also all learning in the following pyramidal structure. At the base of the structure are people in schools, in colleges, in universities who are exploring their lives, being taught various fundamentals, and are curious. And this interaction are the streams of what will feed into the well of knowledge from which society draws. At the next higher level, you have institutions for research or for specific kinds of application, and India has got many of those. You have the Department of Science and Technology, which runs a large number of research institutions. The Ministry of Education, is responsible for institutions such as the Indian Institute of Science, the IITs, and many central universities and other universities. State governments run thousands of universities and colleges. At the next higher level, the country then takes on various kinds of missions, feeding upwards from all of this. And those missions, some of you are very familiar with because they're well known. Space missions, for example. India is exploring another major mission, the Deep Ocean mission, and there are missions in semiconductors and so on. So none of these higher level missions, which have a great impact on society, are possible without the foundations which all of you are responsible for. Now the foundations themselves are not direct. There are many important directed areas of research which people and the government undertake. How can we solve the problem of malaria or tuberculosis or sanitation? Those are all directed problems. But much of what we do as students and as researchers is free and up to us to choose what we want to do. It is this undirected, so-called not useful research which feeds onto everything which we know. And this is true whether it is in physics, or in chemistry, or in biology, or in mathematics. Just a few days ago, a famous philanthropist, Jim Simons, died. And Jim Simons was a multi-billionaire. He had, I think his assets are worth 30 billion or more. And he made his money in a very strange way. He trained as a mathematician, and then he was called to head a mathematics department in a place called Stony Brook. And it was a bit of an out-of-the-way department. But the US National Science Foundation was funding science in a big way, and he built up an extraordinary mathematics school. And that would have been enough work for a lifetime. But in his 30s, he left that and decided that he wants to go into business and into the financial markets. Before he did that, by the way, he worked with another colleague and solved a very important problem called the Chern-Simon problem. Now, I'll come to that again, but he decided to go into the market. And who did he hire to look at the market and see how the market will develop? He hired physicists, chemists, astronomers, and so on. He didn't hire a single commerce or mathematical or financial person. Because he said that people who have their passion to understand something and who use numbers to understand it can deal with numbers in any field. And his company, Renaissance Technologies, made an enormous amount of money. He then decided to give all that money away back into science. And the Science Foundation has invested enormously in science all over the world. And that are in areas such as mathematics, physics, astronomy, neuroscience, and so on. So this is an example of how pursuing your passion, whether it is doing something in science, or building an institution, or starting an industry, can give back to society in unexpected ways. As a pure mathematician, the Chern-Simon's problem didn't seem to have any possible use anywhere else. But another famous physicist discovered its value in an area called condensed matter physics and in string theory. So whatever you do, the kind of work which, for example, Srinivasa Ramanujan did, the kind of work which J.C. Bose did, what Raman did, all of these have got enormous applications now, but the work was done by pursuing what they were interested in and not in looking at what possible applications they had. So in other words, the opportunity to be able to do that is a great luxury. Scientists are paid to pursue what they love to do. And that is a great responsibility also, because if you are given your salary to pursue whatever you want to do, you always keep your eyes open to see how you can give back to society. In that situation, the work which the Agastya Foundation is doing is absolutely amazing and admirable. I don't know how many of you have gone to their campus. It's a phenomenal campus, very beautiful, yet very sparse and one with nature. And there people inspired by nature ask questions about society, science, and their lives, and then go on to do great things. Now I end by saying that one of the biggest challenges India has is the following. In the age group from about 16 to 25, there are about 250 million Indians. A very large number of people in India are young. So unless we open up the doors of opportunity to these young people, we are not doing ourselves or the world a favor. So we must open up that. And therefore, events like this open this up. But in these situations, you must remember that some of us are privileged and some of us are less privileged. The privileged ones have homes where there's time for us to relax and read and imbibe and study and so on, and the others are caught up in the problems of the day. So as students, this kind of a workshop meeting is a very good opportunity for us to meet and interact with each other and help each other. Remember, the friendships you make now and the help you give each other now will last for the next 40, 50 years. And that's the way you will, who are good at something and others who are good at something else, will help each other so that we can work together and do wonderful things. Thank you very much.
Thank you so much, Dr. Vijayaraghavan. The story of philanthropist Paul definitely is very inspiring. Exploring various ideas and options in order to pursue the passion. Thank you so much for that. I request Varshita to step up and hand over our token of the bouquet to Dr. Vijay. Thank you so much. Dr. Anand Suresh, please come over and share your thoughts with these children. Thank you so much.
Thank you, Gaurav. Good morning. And on behalf of the director of IISc, who couldn't be here, Professor Rangarajan, I welcome you all to our campus. When summer comes, our campus becomes very lively because young people come. Not as young as you are. We have a lot of summer interns who are undergraduates from other colleges around the country. And it feels great when you have. Now I feel even more delighted that students as young as you are here. I'm going to be here a couple of weeks. Just want to ask you first, just raise your hands. How many of you knew about IISc before this program was announced to you? Wow, that's great. And I'm not going to ask each one of you in what way you can lower your hands. In what way you heard about IISc? I guess you are spending time here, where our faculty will interact with you. We're going to be spending time in some of our labs, work with our students, and know more about IISc. But actually, recently somebody told me this, which had not occurred to me for a long time. Somebody asked this question: if IISc were not to be there at the time of independence, how would India have been? That's something I want to think about. I'm also thinking about it. There are answers that we can give, similar about other institutions also, but this institute was set up in 1909, long before India got its independence. So after we got independence, what kind of roles you should have played, also similar institutions you would play. I want to think about it as we spend time here. And when you are here, you are going to be listening to a lot of people, a lot of faculty, some of them are here. We thank all of them for enthusiastically participating in this program that Agastya has started. And as I already told, I'm a big fan of Agastya. The first time we all have been to the campus, if you agree with me that it's a fantastic place. In fact, I don't think it's an exaggeration to say that I have not seen such a place anywhere else in the world. So that should make you feel proud that you're part of. It's old, second oldest, not in the first oldest, and something surviving for 114 years. Right? So our faculty are going to tell you a lot of things, and not only you, even when you have executive programs for people who are already working, we have some programs for them. I tell them that when I get opportunity to interact with them, that anything that you take a course in IISc, anything that interaction you have, it's like, fire hose, water comes this big, that fast. That's how the information will come to us. And you are thirsty, we know, but then you cannot drink as much when the force of water that's coming towards you is so big, right? Like a fire hose, water coming through that. Right? So whatever, just get wet and think about what you could do in future. And I remember all my colleagues here also will agree with me that when we were young, mostly undergraduate times, sometimes we used to read papers, research papers, and then later, when we went abroad, most of us did at that time, although now there are people do here also, and when we, whatever papers we have read, when we meet those people, then you understand what you can do. Because until that time you are admiring what other people have written. Now you see these people in their flesh and talk to them and how they think, then you also know what all you can accomplish. I think you have an opportunity next few weeks here to talk to people who have done a lot in terms of research. They are interacting with you, and you can also see whatever you read about in textbooks, what people are doing now, and relate to that. Right? And other thing I would like to tell you is that you are going to hear from faculty from science departments, engineering departments, also here. I don't know how many of you have thought about the difference between science, engineering, and technology. A lot of people get confused with the three terms. Right? We're all going to take JEE, right? Can you raise your hand if you are not going to take JEE? No. Okay, good. Yeah, so you have some other plans. Right? So when you take JEE, you think that you are going to go to engineering. Now there are excellent science institutions also there in India. IISc has, IISers have, some others. You have a lot of options. So science and engineering and eventually technology that you think about, the difference also is something you should actually understand. Okay? So what is the role of scientists, what is the role of engineers, what is the role of technologists? Just to make it very simple for you, I would say oversimplification, I would say that science bites. An apple is a classic science for Newton, right? It bites. It then leaves it. You find something interesting, and then engineering comes along and chews that. Just bite and then chew. And technology digests. You have to understand what you want to do, right? And what you want to do should be really ambitious. When you are privileged and you get these opportunities. I was just talking to someone about the Gaganyaan program, which was also mentioned by Vijayaraghvan already. When you think about space, you should think about human endeavors. Right? In some sense, humans first have, I would not say conquered, at least took control of the earth. And then it was the seas. Not the deep seas, which he talked about, right? At least seafaring was made possible because of adventurers and a lot of people who are interested in, who are curious about what other parts of the world have and how to get there. And then it's the air and space. Right? So we all take the flight for granted now. Right? What's the next thing? So that's what probably you should think about. Right? Next thing probably we should be able to go to the moon and come back and do all the things. Right? In space, manufacturing, a lot of things have been talked about. Then your generation can dream more than what others have done. Okay? So pay attention to what you want to do. It's difficult to decide at this point. Normally there are stereotypes. If you build something Lego blocks as some mathematics, people say your parents or somebody would say you're going to become an engineer. And then you do something that's interesting, people say, oh, you're going to become a scientist. You don't have to classify yourselves as scientists and engineers and technologists. In fact, Vijayaraghvan himself trained as a chemical engineer, now he's a molecular biologist. Right? So you don't have to worry about it. Just be curious, do what you want to do. Wherever your heart is, you can go there and do well in whatever exams you take, but you should not stop there. People always say curiosity. And I want to give one example, again, something Agastya has done. There is a series called Remarkable Indians. I think Navodaya has seen on that, those videos? We will not. Yeah, have you?
They should.
Right, they have. So, I think if you watch those, I want just do one example. There is one by Professor Manu Prakash, who is a professor at Stanford University. I was amazed when I saw that video, his interview. There are a lot of people, a lot of amazing things that in that series what people have said. I think you should watch. It takes time, each one is over an hour. But you choose in your spare time or whenever you want to tune into that mode of thinking, relaxing, I would say. There was one example that when I was a young boy, he was surprised to read somewhere that a rabbit has almost as many bones as a human being. You probably all know the number, how many bones are there in a human being, and probably a rabbit also. He was surprised, why should a little animal like rabbit have so many bones? It doesn't do as much as humans do. He was very curious, he could not believe what he read somewhere. He actually went to a butcher shop and asked the person there to give all the bones and that, skeleton. Obviously, the young boy goes and asks, somebody will be suspicious. But somehow he convinced that he was curious. Actually, apparently he did that and counted and convinced himself that there are bones and probably thought why there are so many. Right? That is really curiosity. Of course, you hear somebody talk, you can raise your hand and ask a question. That's important. But sometimes curiosity has to go a little farther if you actually want to extrapolate what you will be many years from now. Okay? That's something that you can cultivate and ask people similar experiences. The faculty that you are going to meet, if there is time, you can also ask what drove them to what they chose to do. That will give you an idea of what you can be Again, you don't have to decide that today. Right? We are good and in a good group, where you go to a good place, where there's a good environment for learning. You can do all that. So, exposure to what all you can become, what all you want to do in different places. Hopefully these 2 weeks will be very productive in IISc. I wish you all the best.
Thanks so much, Professor Anand Suresh. There's a story I want to share, and I heard it from Professor Anand Suresh some time back. There was a boy in grade 9 who was, that day the teacher wanted to teach optics. And he asked the boy to go to the lab and get a convex lens. And the boy went to the lab, asked the lab assistant, the teacher wants a convex lens. The lab assistant gave him a convex lens, and the boy said, no, I need a convex lens. The teacher asked for a convex lens, not this. And then the lab assistant said, go ask your teacher and get it in writing. This is convex lens as far as I know. So the boy goes back to the teacher and says, the lab assistant doesn't know what convex lens is. He wants you to give it in writing. So the teacher gives it in writing, and the boy goes back to the lab and asks the assistant saying, this is what the teacher wants, I told you. And the lab assistant once again gets the convex lens that he knows and gives the boy saying, this is convex lens, take it to your teacher. The boy refuses. He goes back to the teacher and calls him saying, the lab assistant doesn't understand, you need to come. So the teacher goes with the boy to the lab, and the lab assistant hands over the same convex lens. The teacher takes it and says, this is convex lens, why do you think it is not? And the boy says, this is circular. You always talked of convex lens as, this shape, the shape of a third eye of Shiva or something like that. So how can this be convex lens? So that boy, if I remember right, was Professor Anand Suresh. And he narrated this story to say how important it is to really feel and do experiments yourself. If it is just theoretical, you just wouldn't know. I can't forget that story, Professor Suresh. So next, I invite Shri Gopal Krishna to come and.
Does he not get a bouquet?
Of course he does. Sorry about that.
You're penalizing him for getting the answer wrong.
I got carried away. I got carried away with my stories that I heard from. Pamni, can you just step up and hand over the bouquet to Professor Anand Suresh? And thank you, Dr. Vijay Raghavan, for pointing it out.
I also want to know how you remember the students' name.
I have been with them for the last 4 days. And they were on the campus. And we had a wonderful time.
It's also a rule in this program that people who enter this program must know the children's name.
I think he deserves a bouquet for that also.
It's my experience, and even since the days when I've been running the school, that when you address the students by their names, they respond far more. That is not just a student, anyone. Shri Gopal Krishna, please come over and address our children. Thank you so much.
A very good morning to all of you. Most respected dignitaries on the dais, my dear staff members and principals, vice principals from IIS, and the team Agastya, and my dear children. In fact, this is a dream coming true for me. Bringing our Navodaya children to be part of this Science Enrichment Program. And Ramji sir, you have given me the book titled Moving the Mountains. This is part of it.
Oh, great.
Moving the mountains and bringing the best of the best Navodaya children on board with this Science Enrichment Program is a very big success. It's a It's a great beginning for a better journey. Respected dignitaries, I just very briefly I would like to place before you that we, Navodaya Vidyalaya Samiti, having 649 schools across the country, one in each district, we conduct an admission test with the help of CBSE or any other agency. Around 25 lakh children appear for the test. Out of that, around 53 to 54,000 children get selected for 6th standard. And the competition ratio is approximately 1:55 to 60 in average. And out of that, now these children, we have 28 children from Navodaya background and from other schools also we have some children here. They have been selected through various parameters. So this is an attempt to bring the best out of the best. And that's how this all happened. And we have a girl child from Anantnag, we have a girl child from Andaman and Nicobar Islands, and we have across the country, from children from across the country. 3 children are from Shillong region. So it was a great attempt on the part of Agastya to select these children and bring them here. And I'm sure this is going to be an amazing journey. And these children, when they go back, they are going to be the real brand ambassadors, because we are already on the active path towards experiential learning, creating learning spaces outside the classroom, learning while doing, learning for life. All these things have become part of Navodaya education system. And right from its inception, we have been working on it. With our association with Agastya, a lot of modifications have come in our way of thinking and our way of implementation at grassroots level and things like that. And this particular initiative is going to be a great journey. And I'm sure whatever support, our commissioner was very much willing to come and participate in this program. Due to some administrative challenges, he was not able to make it. Sir, take it from us that our association, our support, anything that is required from Navodaya Vidyalaya Samiti, we are always there with you. And let us go beyond what anybody can think of to create a better universe with the help of these children. Thank you, thank you.
Thank you, sir. That was indeed very encouraging. And we do have really ambitious plans going forward. We are extremely delighted that even with a very short notice, we got such a great support from JNV. And every one of them, every one of the students here, a gem and a future promise. We got their support, their willingness, and their keen interest on joining this. So thank you so much for the support. Request my train to come over and hand over a bouquet of flowers to Shri Gopal Krishna. I just also wanted to share that while the majority of the students, a very significant majority of the students are from JNV, we also have a few students from other schools, just to create a very rich mix and ensure that these, future grades, if I may say that, because I'm pretty sure you would be, interact with each other and establish what one refers to as the old boys network or the old boys school network or whatever. That can be much bigger than just your own school. So, wishing you all the very best. I wanted to, is there anything, Ganu, you wanted to share? Before that, I would just invite if any one of you has any question or any point you want to share with our guests here. Maybe they want to answer, maybe they spark something. You're most welcome to ask that. We have a few more minutes and then I'll hand it over to Ganu. He wants to share something with you. Yes, Pratap.
You need the mic?
Yeah, we have a mic. Hello.
Namaste. Sir, like I wanted to ask, that why did you shift to molecular biology from chemical?
So, first of all, I should say that, chemical engineering is an unusual kind of engineering. That when you study, you learn a lot of fundamentals of physics, of chemistry, of mechanical engineering, and other areas also. So it's in some ways a mixture of various kind of processes. Now, the result of that is that over the last, since the early 20th century, many people went into chemical engineering because their parents told them that's where the jobs are. But when they went into college, they found that their interests were different from that reason that you want to go in and do something because there's a job. So when I got into engineering college, I had to choose between electrical engineering and chemical engineering. And my father's friend came and said, do chemical engineering, there's a great future in plastics. That's also a famous line from our movie. So I have no particular love for chemical engineering or dislike for it. So I took it because someone told me to do this. Then when I went to college, I was exposed to a lot of physics, chemistry, but no biology at all. I've never done any biology. But I was fascinated by the brain and the body and how it works. And because I didn't know anything at all, I had the courage to start my PhD in biology. If I had known how difficult and complicated biology was, I would not have gone into it. So ignorance is also a good thing. Once you go into an area with ignorance, then you don't hesitate to ask stupid questions. And if you ask stupid questions, then you open up interesting avenues. Otherwise, you tend to stay in the rut which others have created. So, it's all accident upon accident, but I'm enjoying myself.
Anyone else? Thank you, sir.
Sir, I have one, maybe it's not a question. I just want to say, all of you talked about the change you want in education system, more about focusing and observing rather than cramming up things in our mind and just reading them out from the books. But in our schools also today, we do that things. We don't go to laboratories often, we don't do experiments often because our teachers also focus on the results more, the academic results we have. So, what can we do about that? About the Navodayans maybe, because majority of us are from Navodayas on. And the Agastya schools, do they focus more on the observing thing we did at the Agastya campus, or is it same there also?
On campus or the Agastya schools?
So the things we did at the campus, like the experiments, and we didn't, read things out from books only. Are the schools also like that?
Yeah, increasingly. Yes, so what we are doing is, one is working directly with young people like you, okay, because you need to start using your senses more. The other is, we work through teachers. So we have a very active teacher training program. We get some 2,000-3,000 teachers from around the country who come to our campus, and they go through a program called constructivism, how to construct knowledge from first principles. So working with students, working with teachers. But then we found that's not enough. There's a very outstanding educator who's no more. He was teaching at a famous school in Bangalore. He quit and started another school. Outstanding, I was told. And then he left that school and started a third school. So I asked him, why did you leave the second school, which had such a great reputation? He said, I got one thing fundamentally wrong. We have the best teachers in the country. They really absorbed this philosophy. They're the best. But all the great work they were doing in school was undone by the parents. Right? So in Agastya we said, look, we are focused on children and teachers, but there's another important leg, that's parents. Now we can't go and teach science to parents, we don't have that capacity. We're talking millions. But can we make them more aware of what the children are going through, why that is important and so on. So it's really three components, right? The head of the institution, see, why is this program growing? It's the point I wanted to make. Nothing great will get done unless you have a great champion. In any field. Now here we have a great champion in a very modest guy. That's Ganu. Okay? Without Ganu, this all isn't happening because of me. I know next to nothing about how to nurture kids like you. So you need a champion. So any institution, whether it's IISc, and I'm sure Anand Suresh and Vijay Raghavan can talk to it better than I can, you need people at multiple levels who drive it. So working with teachers, working with parents, we would like to start a program for headmasters because their job is different. It's about change management, about creating an environment. But as Mr. Gopal Krishna was saying, that some of these ideas are now permeating. Am I right, sir? They're permeating. You've got a person like him who's very open to this. So I'm sure you'll start seeing changes, even the new education policy. If I'm not mistaken, addresses a very fundamental thing from what to think to how to think. It will take a bit of time, but you shouldn't wait and say, look, teacher is not doing this, I'm not doing that. Use every opportunity you can, whether it is here. See, it's not how much time you spend doing something, it's the quality of the time. You're 2 weeks here, you're going to spend 2 weeks, it can be life-changing for you. And similarly, your 5 days at the campus. If you're open-minded, then it doesn't matter what any system is. You will transform as an individual. And then when the opportunity arises, you will shine. So don't be, be optimistic. But use this opportunity like a dog with a bone. Do it.
Any more? Okay.
Is there any difference between the IIScs and the IITs? Is there any difference between the IITs and the IIScs?
It's more like a parent and child relationship. Probably the IISc is older and IISc is afterwards. And the first IIT, which is the first IIT, our director, so it just is older and that's but then having said that, we have a value program we had ESC master program there for some time. The IITs were really meant for beginning of the setup. But they have come up, they are doing research, now we are getting to the graduate program. So right now I wouldn't say that there is any difference. But the way this institution has developed, in first year, there is more emphasis on research. So even when our master students come and they are getting an MTech degree, but they will do a project, which most often we use that as a way to try out our research ideas. We don't do PhD students. Because with grad students, limited time, there is not much at stake. If I have a really crazy idea, I would not want to give it to a PhD student to write out. We write out on master students. And in our BA program, part of our UG program here, I think our faculty will do that. We try out on you. Because there is nothing at stake. You may do a degree, but we can. So there is this research emphasis. I'm not saying it's not in IITs, it is being there for longer. So whether we are starting 3 more BA programs starting 2025, which is available to you. Right now we have BA program in mathematics and computing. And 2025, next year, we are going to start in aerospace, mechanical engineering, materials engineering. Right? So the science program becomes BTech program. Science engineering. Okay, the short answer is that it's just that it's older, everyone is done research. But these are also pretty old and they also have research. So it doesn't really matter. I don't think you make the mistake to choose IISc. It all depends on what you want to do. You want to do daily science here, you have science undergraduate program, that's also the daily. You can do that. You get to learn different aspects of science. Now we have BTech program. But then we are going to have a lot of interdependence between the two programs. In fact, we used to on our campus, we see two sheets there. One side is UG complex, other side is BTech complex. We call it, but I said you run with that. You get to actually experience because you have both scientists and faculty. It's also hard, but it's just older. So I will start with what I said, parents and
Teachers, do you have any questions? Someone else here? Okay.
Sir, I have interest in bio and physics. Can I join here? Yes.
You have major and a minor. Our undergraduate program, you don't have to clear your major. You don't have to say, I want to choose biology or physics or chemistry. After 3 semesters, you get to say what you want and so there's a major and there's a minor. So the biology or physics.
Can I enter through NEET, sir?
I think others are there.
Through
NEET
GATE.
is also there for undergraduate program.
Through GE.
NEET is not there.
Through GATE.
CE. Yeah. JE. One of them, either of them. No, it's the same program. The admission is to both. It is to KVBY also, but that's not there now. We have other days. JE also. JE also you can apply for that. Both are both. But this
One or the other, JE or NEET. You don't have to have passport.
As Puna ma'am said, there is a lot more information on the websites of each of these institutes. Recommend you check that out thoroughly. What options are available, what you could pursue, and how can you tie that to your interests. There is much more available on the websites, so recommend you check that out. Anyone else? Any other question? Yes.
So my question is a common question, like, does those Indian mythologies like Ithas and Puranas have a scientific explanation? Like some recent researchers, right? All these have been written now at Ithas also. So why is not anyone referring to all these things? Like the Pushpak Vimana, we have been reading in Ramayana, right? Like it's basically like an aeroplane that we have been invented in these decades. So all these books would have been a reference for us, right? For any advanced technologies.
Yeah, I'm happy to answer it. See, one must not mix up imagination with reality. And you can have an imagination of many kinds of things. They can be inspired by your history, your scriptures, and your civilization and so on. But to assume that that is reality would be a mistake. Right? So, for example, sitting today, you can imagine that there will be space travel across various planets. Supposing 200 years later, someone does that. It doesn't mean that you invented space travel. You thought of it, right? And you thought of 200 different things. So thought is easy to, and imagination is easy. But to assume that that is reality would be a mistake. Second point, there are many wonderful things which have been done historically in our civilizations and other civilizations. But they are open for rigorous questioning and examination, just as current science. The key hallmark of a scientist is not to accept something, but to question something. To say, why is this not correct? Supposing I tell you that, if I unscrew that fan, it will fall down, then you must ask yourself, is that true? Why does it happen? What are the rules which allow that to happen? Why is it staying up, not falling down now? Don't just take it for granted. There are many things in life which we read about in our textbooks, in various religious books and so on. But each of them has a different purpose. Textbooks, whatever you learn, and your course, whatever you learn, is up for questioning in a rigorous way. Right? Other books have different purposes. They stimulate your belief systems, your faith, your peace of mind, and so on and so forth. Take those as literal and equivalent to this to be completely incorrect.
But also I would like to ask at the same time, is it science fiction? Yeah. So there are a lot of imagination in science fiction. It's exciting when you read it, but not in reality. Right? But some of them can be, but there is no evidence that is so or not. So the thinking practical way or rigorous way to see what you can accept and cannot accept. Imagination is important in research, but it has to be grounded in whatever we know.
Thank you. Anyone? Anyone else? Any other question? Okay, we still have time. After Ganu shares whatever he wants to, if there is still time, we will take the question. Sorry, you can stand up and ask.
So is there any possible way in which I could get to IISc or IIT without giving an entrance examination which thousands and millions of other students do?
Lots of faculty members have not gotten through the exams.
But what if, supposing he created or invented something, was an IIT or IISc, say, forget the exam, look what this guy has created. It's really innovative. We'll take it. Would it? I don't know.
No, I think there is no shortage of great institutions in India and abroad who will do that. But I would be very careful in aspiring to that route. Because people who do great things don't say, I want to do something great, let me do that. They say, I'm very passionate about this, let me try it. And there is a consequence to great things. But if you say, I want this prize, I want to do great things, I want to get into IISc without an entrance exam, so let me try and prove this theorem, it doesn't work there. Because whatever you need to do requires both a combination of talent and hard work on one side and extraordinary luck. So to think that all three will work out according to your plans is very, very, very hard. So it's important to let you know, our student from Maharashtra, she asked, well, what about studying in the rut and getting trapped in that, and you say, look, innovative way, look around. Now, the point is, studying in a routine manner, which your schools say, is useful because it promises you a buffer, allows you to make sure that you get certain kind of job and earn a living. Point which Ramji made is that should not be the all of your life. In addition to that, make time for quality pursuits. Quality is important. You need to make sure that you like and do something which you enjoy, whether it's sports, music, mathematics, or science, or history, and do well at it. Some of us are gifted, we're very talented, and very few of us are like that. Right? Almost nobody, it's such a small percentage that those people stand. Those people will find ways, or the system will be accommodated. away and I'm a genius and accommodate me. Should not be a plan.
Thank you. Ganu, please come over. Hi. You can't get rid of me, right? Moral of the story. I will always come back. So, first thing is, I want to say thanks to Anand Suresh and IISc faculty because about maybe 3 months back, this program was not a reality. Nagarajan, I shared my foundation and I walked into Anand Suresh's room and said, this is the kind of program we want to enable. We are ready to take us to another colleague at lunch. And then we also met the director. So we made a pitch. And nothing happened to the pitch. You want something? You got to ask for it. Okay? So you pass it, you chair, and let good things happen. So we made a pitch, and it turned out to be a successful pitch. And they were all together. The second thanks is to our partner, the Asa Foundation. So you saw a member of the interviewing you, Mahesh. And there's also another person, Kailas, who is the director of our foundation. She couldn't be there. Because of the very same reason, 3 months back was not reality, and they had already committed themselves to some programs, right? So they could not come back from there. Our thank you to you and others, like Professor Vijayaraman. How many times can you send a WhatsApp message to someone who's traveling to the US? Sir, we have this particular inauguration, we'd like to come and inaugurate. You just send WhatsApp message back. I'll be back on such a day. Let me check the calendar. Okay. Not us, right? But you have to ask. Okay. Simply say, oh, they send an email and so on and so forth. Perhaps you would have lost, and I would have lost once again to listen to Professor Vijayaraman. He also reminded me of his unusual journey from chemical engineering to biology. Another senior of mine in IIT when I passed out, I was like 18 years old perhaps. And in the first graduation, somebody said, the most loquacious, very eloquent speaker, the literary secretary of the campus, I call Shankar. We all have campus hero, right? So Shankar, what is he doing after graduation? Somebody said, he's going to Caltech or Illinois, or which one, to do physics. I just could not understand why would an electrical engineer want to do physics. I did not have the imagination, the resources to think about it. Eventually, we landed up as the head of physics department in Yale. So you are still young. What you think you like may not be the thing that you develop a deep passion and love for in 3-4 years. Okay? So keep your curiosity alive and keep looking for that which you can commit in the next stage in your life. Don't worry about lifelong commitment. Even Chandrasekhar, as an astrophysicist, I have heard a story told that you concentrate on one area of astrophysics for 6 years, make some definitive contributions to that, and move to the next area. Nobody expects you to stay in the same area right through your life. But developing sharper powers of observation, sharper powers of question, being able to ask scientific questions are some of the things we hope you will learn in this campus through your experience here and also through osmosis. You simply interact with a lot of people, you get a lot of GV by osmosis too. Don't rule out that process. I think you don't have to do yourself. Somebody will help you if you ask for it. So with that, I'm hoping that we will have a fun time, and I'll be here again, listening to all your classes, and take notes on who is asking questions, who is not asking questions. Okay. So be careful about your silence. Somebody is watching. Right? Thank you.
Thank you, Kanu, and thank you, everyone. We will take a break before we start the other sessions.
a brief 10-minute break, this function comes to a close. Thank you so much.
Fellow of the Indian Academy of Sciences, Fellow of the National Academy of Sciences, India, Fellow of the Indian National Science Academy, and Fellow of the Royal Society of Chemistry. He finished his undergraduate and postgraduate education from Madurai Kamaraj University, Madurai, Tamil Nadu. He obtained his PhD from the Indian Institute of Technology, IIT Madras, in 1990 under the supervision of the late Professor J.V. Subbarao. His research focuses on inorganic solid-state chemistry, specifically in the synthesis, structure, and mechanistic studies of framework solids. His work includes investigations into magnetic interactions in low-dimensional solids, heterogeneous catalysis, photocatalysis, ionic and electronic conduction, and lithium-ion conduction. Dr. Natarajan has made significant contributions to the development of new materials with applications in catalysis and sensing. Please join us in welcoming Dr. S. Natarajan, whose insights and research have had a profound impact on the field of solid-state chemistry.
Working up to a point, I checked everything and then came out. Okay. Thank you very much for the introduction. And in this lecture, we will look at chemistry and upon the following lecture we have to go through the and where actually the chemistry begins as a science subject. Anybody know? Any idea about it? Chemistry as a science. I tell you that of all the science subjects what you have studied, probably chemistry is the oldest scientifically investigated subject. And before it actually became science, there are many other ideas and theories which have been floating around. And if you look at why I mentioned the chemistry as the oldest practice in science. One is, before you think of chemistry, people looked at it what's called alchemy. The idea is to convert an element into gold. Why gold? Many precious. They are much more precious than gold. Rhodium. Rhodium is the more expensive. The most important quality of gold, gold is one element you can mine it as gold. For all your elements of the periodic table, majority of the elements has either a sulfide or an oxide, nitrate, carbonate, any one of them as a source. Gold, okay? Of course, gold also has minerals. It's not that gold doesn't have minerals. Okay? So, people were fascinated by gold and wanted to go and then look at how we can convert any other element into gold. Because the gold was beautiful, it was looking good, people were using it for ornaments, etc. Okay? And there are, associated, somebody mentioned about slightly lesser reactivity compared to others. So, it's not easily, you can't use gold, for example, it is not easily reactable with any acid, other than alcohol. Or, if you think about gold, it's not going to react with water, it's not going to react with. And if you are thinking about that, then what happened here? One of the things is, they were looking at a base metal into gold. And the idea is, if it's possible, transforming, for example, lead into gold, and if you think about it, lead as an atomic number is larger and gold as an atomic number which is lesser. So if you want to convert an element which has got a slightly larger atomic number into lower one, the difficulty is almost impossible because unless you carry out a nuclear reaction. And it is Glenn Seaborg, just to show that if you look at the trans-uranium element in the periodic table, Seaborg probably contributed something like 13 elements of the periodic table in the trans-uranium. Okay? And he succeeded, if you look at it, transforming lead into gold by removing some protons from it by hydrogen nuclear reaction. And of course, I just, because many of the students are there, element 106 have been named as seaboard here. Okay? And so, what was the outcome of all these alchemist approach? There's a lot of random thought and there are a lot of random ideas about the reactivity of different available at that point. So most of the time, you know very well that the bronze is known for a long time, brass is known for a very long time, and people have used iron for a very long time. That's for at least 1,500 years. And if you are going to look at all that, we needed to move away from there into some kind of scientific ideas. Okay, so there are a lot of information was floating around. And what is going to be the history side of it? When actually people started looking at it. The earliest idea of anything which people thought that would be closely related to chemistry, then the first ever approach was something called the phlogiston theory. What people at that point thought, we are talking about at least 10,000, 1,200 years back. It's kind of. And people look at the phlogiston, well, if you look at, today we know that you take a wood, it burns. But why should the wood burn? Because it has got carbon, it has got hydrogen, it has got oxygen, it has got nitrogen, cellulose, all kinds of things. So, it burns because it can't convert it into carbon dioxide. But the idea people have at that point of phlogiston is something which is going to burn. So, and it gets released during the burning. Because if you take wood, participating released most of the time with steam and CO2. And people even believe that what we are breathing out, and then eventually when all the pollution was consumed, you get into a situation where the man dies. And these are some of the earliest ideas about, because what people thought in those days, even to convert an element to another element, you have to burn something. So burning is something which is fundamental of transforming one matter to another matter. And so people thought burning is going to be a fundamental process. And the science, we can say that the study of related to the burning or with respect to the gases. So when I talk about gases, who do you think? Who is the first person who talked about gases in chemistry? Sorry, should be there in the 7th standard. History was there, they come. History was also there. First, the following is somebody was to start. First person is Robert Boyle. Boyle's law. Boyle was the first ever scientific study in chemistry. Okay? In terms of law, it was the first one. So if you look at Robert Boyle, yes. And Robert Boyle not only, he looked at what happened, the relationship between the various ideas on pressure, volume, etc. And he also proposed a combination of small particle into a molecule. And more importantly, the contribution that Robert Boyle did, more than the gas law, was to create a forum where free exchange of ideas can be carried out. For example, in those days, it's not like a particular chemistry laboratory where you can do an experiment, people do it in their own houses. And when you do that, you come up with something, you need to share and discuss and see the validity of that particular idea. You need something. So he was a founding member of the Royal Society in London. And Royal Society even today is the oldest functioning, even today, the scientific body in the world. Okay? And second comes, in terms, because we are talking about gases and everything related to gases comes to play, Joseph Priestley. And why Joseph Priestley? I have already listed out 3 important contributions of Joseph Priestley. One is oxygen, carbon monoxide and carbon dioxide, as well as nitrous oxide. And I am not going to take the history into the 19th and 20th century, because many of you will be aware of it. I am going to talk about till about the early days of 19th century. So, if you look at oxygen, but how did he know that there is something called oxygen? And before we go into that, who actually called the gases oxygen? He's also known as the father of chemistry, even today. Yes. So the person who actually, because see, there has always been within the Europe, there is a lot of interaction between different countries. So the person who actually, he carries out a lot of experiment. And how do you think Joseph Priestley identified a gas, totally about whether he called it oxygen or not, because he didn't. That name was given by Antoine Lavoisier. And Lavoisier even today is called the father of chemistry. Okay? Because he identified the gas, what Joseph Priestley called it air, different form of air. He did one simple experiment to identify that there are air containing different compositions. Okay? So one experiment what he carried out was, today it may look very cruel, but thing is, so he did this bell jar experiment, where you put everything hermetically sealed. That means that any external gas cannot enter or go out. So there is a fixed volume of gas. And when you have a fixed volume of gas, you put a candle, candle starts burning. After some time the candle stops burning. You know that stopped burning mainly because it consumes the oxygen and converts the CO2. And when you have no oxygen, you put a living species, it dies immediately. Then, this is something which all of you have to know. It was not that Joseph Priestley did one experiment and then said, yes, okay. He carried out a large number of experiments. Look at the second experiment. He also looked at the same experiment where he did the same experiment. The mouse was about to die. He removed the whole plant and then put it up in the, along with the plant with the mouse. The same culture. So that tells that something in the plant actually converts something which will give rise to a new type of air, he calls it, so that the mouse is alive. Today we know that process called photosynthesis, where the carbon dioxide which is being produced by the burning of the candle and the carbon dioxide is being consumed by the leaf, releasing the oxygen back. Okay? So we talk about many other things today about greenhouse, etc., all that. But the fundamental idea actually arrived from the Joseph Priestley experiment. He has not stopped with only these two. So, for example, he also did experiments with mercuric oxide. Okay? So, photosynthesis he has done, and then he did a mercuric oxide. And mercuric oxide, if you heat it, and mercury would come out and oxygen will be released. And then you look at, he wrote this book. And if you look at the title, the experiment and observation of different kinds of air. He never ever called what he found as oxygen. And of course, the experimental details, what he has carried out, he has always been in communication with Antoine Lavoisier. And it's Lavoisier who actually called this one of the things what we call today as oxygen. He gave the name. Okay? And next comes Lavoisier, because Lavoisier and Priestley discussed about the new gas. Lavoisier who called it oxygen because if you look at it today, it looks strange, but in those days, you are looking at something in the beginning of the 18th century. If you look at, he called it because in Greek, it's an acid maker. Okay? Because it combined with non-metal to produce gases. C plus O2, CO2, S plus O2, SO2. Every one of those gases, when it dissolves in water, definitely produces an acid. But of course, today we know that you can take sodium and heat it, and then from sodium oxide is dissolved in water to oxide into this. So we know it much better, but that's the thing which stayed. So he's considered the father of chemistry, and he found that hydrogen burned in air to produce water. Because today we are talking about hydrogen economy, green hydrogen, etc. But the idea actually, if you think about it, it all came about much before. They are not going to be able to years back. And he introduced metric system, and he did a lot of other things also. Okay? And of course, this is something for, since we are talking about history, we have to talk about who was killed by Bellagin, mainly because job was given by the king that he has to collect taxes from the common man, and anytime you are looking at collecting taxes, you are always going to be in the negative light in people, and when the revolution, French Revolution happened, he was killed. Then, so we will talk about a few of them here later. And around the same time, if you look at all the years, it's all overlapping significantly within themselves. Alexandra Volta. Why I am mentioning Volta? Because it is a completely new idea, like what the Joseph Priestley's idea was when he talked about different types of air. So he talked about how the different types of air comes up. Similarly, the Alexandra Volta, or what we call the voltaic file or the primary battery, okay, that is become very, very important discovery because and that why it becomes very important later. Of course, Becquerel is the man who actually talked about stoichiometry. Why should one carbon and one molecule of oxygen to react to one molecule of CO2? Stoichiometry is an idea given by Becquerel. Benjamin Franklin demonstrated that lightning is mainly due to electricity. There are many other things of Franklin, but I don't want to get into the detail. And of course, you know about Avogadro, and then Humphrey Davy has spent some time, and Gaiusa, who discovered many other issues in history. Okay? And if you look at why Volta becomes very important. So just to think about two different elements, copper and zinc. When the copper and zinc, Volta what he did, he actually put a sheet of the sheepskin soaked in acid. So he put the sheepskin in between the pile of the copper and the sheepskin and then zinc, then again sheepskin, it goes like that. When we do that, then he realized that when he connect both of them to the original picture of the Volta, what he created is shown here from the museum. Okay? And once they realized that there is some kind of electric charge, you know, thinking about something of an electric charge 200 years back is a phenomenal idea. Okay? Something to talk about, there is some voltage differences which are being created between two dissimilar elements. And of course, I mentioned that along with at that time, the precursor to Volta was another guy, Italian, who actually came up with the idea, and but he didn't do the battery part of it. Galvani, Galvani, he did the frog experiment, put the two frog legs, etc. These are very important. He actually started the idea, the Galvani is the one who started with the idea of the electric charges. Then he came up, picked up by Alexandra Volta, and then created the Volta coil. But Volta created this, and you know, never forget that even today we call it any electrical voltage comes from here. Okay, the volt comes from here, Volta. Okay, so he does not know what to do with this discovery. That was now, of course, by the time it spread all over the place. Then we have.
So why did you put leather sheets over an acid vinegar?
Then nothing else is there. What else you will put to separate the two both the metal?
So why do it acid?
You need an electrolyte. Okay, I didn't have it here. I have a video on how you can do it. I will tell you how it is. What you have to do is you need to get circular disc of zinc. Circular disc of copper.
You could have chosen any other metal also.
It could be hard. See, you have to look at how many different metals you know. Here I am going to talk about metal. How many elements are known in IISc-Agastya? So you know there are many other elements. And when you look at copper and zinc, people have been using for brass. You understand? So people know about all the reactivity, etc. They have been there for years. So you have two metals. Even today, you can put one nickel and copper, one zinc, just a disc. What you do is you cut a ordinary newspaper, what you buy. Have a small amount of water, put sodium chloride. Nothing else, just sodium chloride is put. Preferably in saturated solution. Put the paper, put that. So stack it up 5 times. Put an aluminum foil at the bottom, aluminum foil at top. Connect it to your multimeter.
Is it admixture or base?
Any inside a strong base. When you are looking at a strong acid and a strong base, what you form would be neutral. Okay?
It was like a salt bridge.
It can work. The thing is, what we are looking at here is when you are looking at what happened after some time. Repair the primary battery. The main issue with that is it dies after some time. It's not internally working. Okay? That's a problem because it stops being conducting after some time. That's what it. You can always report it. You need to keep it reasonably good. See, one thing what you can do is what is really already right. Just check what is inside. You see a central graphite rod, and then you will have a circular. When I was young, I don't know what they are doing. I have done it with a zinc metal. Okay? And if the zinc metal means you have it, and you have a lot of carbon. And then they put some chlorate, etc., to have chlorate, etc., which will keep the moisture inside, so that you can have positive or negative, you can have the current coming out of it. Okay? And that is why they say that don't throw the battery into fire. Because you have your perchlorate saw, boom, it goes off.
So how did he come up with the idea of putting those things in between? He could have just started them up like zinc, copper, zinc, copper.
See, the one thing which the earlier Galvani experiment said that we needed to have some kind of liquid in between. The Galvani experiment, between when you put in a strong lead, very strong but cut. Okay, Galvani experiment. And then when you put two electrodes on both the legs, okay, the body switches. They get from. That is the Galvani experiment. So he realized that you have to have some kind of an electrolyte. So if you are going to have some kind of an electrolyte, what kind of electrolyte? Looking at the years, we are looking at 17, 18, 27, 26, something like that. When he died, so it's about 20 years before assuming that. We are looking at 17, 19, 17, 18. Okay? So at that time, the amount, what you have today, you have to think back. They don't have electricity yet. They are not from the electricity at all. So the number of elements known as very limited. I put daily. Okay? Daily has put earlier put some 8 elements. Okay? And we are not even come to daily when we are talking about water. So the number of elements known, probably iron, copper, zinc, probably some nickel, a few very small number of elements which are known. Of course, in terms of other side, they will have sulfur, they will have carbon, they will all those they will know. Okay? So that is the problem.
In the diagram, in some places the zinc and copper are stacked without any seepage in between the layers.
No. You can't have it. How can you have it?
This is see that it's level 2.
This is one battery. You understand? One stack, positive, negative, copper, zinc. Copper, positive, zinc, negative. Okay? Copper, positive, zinc, negative. This is your leather in between. So this is one battery, you are stacking one after the other in series. Okay?
Sir, but why were two metals selected as zinc and copper instead of using one metal twice? Why were two separate different metals selected for each layer?
See, there is something called electrochemical series. You will study later. Okay? If you are looking at in the periodic table, okay, each one of them, for example, if you take sodium, that has got a different reactivity compared to copper. Sodium you cannot keep it outside. Similarly, copper you can keep it anywhere you want. So each one of them, there is something called electrochemical series that tells you about the reactivity of different elements. Okay? So it depends on how easy to get an electron, how easy to donate an electron. Okay? So that series will study next year probably. That's what the time to know. You will see that. So people, the
Sir, I want to ask a question from the previous topic about alchemy. You said that when Sivo was succeeded in making gold, so then why we don't use that method in present time? We are succeeded in making gold.
You get to gold.
Yes, sir.
The amount of cost involved is gold that important. Is gold that important? Don't worry about jewelry part of it. Other than that, where do you use gold? Gold is very limited use because somebody mentioned over there, less reactive. It's not reactive. It can use as a catalyst, but the thing is, at the cost of what? In a catalysis. What is it you want? You want to reduce, why you want to use a catalyst? You want to have a process A plus B equals C. You want to reduce the cost as low as possible. Right? You don't want.
No, I mean we use platinum as catalyst. They are really high in cost.
You know how much? I know how much they use. Same thing with gold also. The amount of platinum we use is fraction of a percentage.
Why are scientists trying to make something that they can replace platinum?
We have developed a lot of other catalysts also. See, the issue is most of the time why people go for platinum or rhodium, which is even more expensive but more used in catalysis. Mainly because these are elements stable under steam. See, when you are looking at any catalytic process, you are looking at 400, 300 to 400 or even 500 degrees centigrade. And some of the product of the catalytic reaction will be water, steam. So many things will degrade. That's why they are looking at a noble metal. Okay. So coming back to your question on you have to be a nuclear reaction to remove protons. The amount of energy you have to give it to remove the proton. It is just to show that it is possible to see more. Okay. But the amount of energy you have to give, say, you are going to get, he actually created 8 atoms of gold. Just 8 atoms. They are doing this nuclear reaction. Whereas if you want to know, if you are going to look at Avogadro, and then you are going to look at a larger quantity, you need a lot of. So the amount of energy you are going to expand to make that gold, then the gold, what today is, I don't know, assuming that 10,000 rupees per gram, it will be 10 lakh rupees per gram. So it is becoming unaffordable and people will know it. That's the reason why people have not attempted further in any of those kind of studies or converting it.
Sir, I have been connected with some local people who are also like from reading text or Asian text doing the same thing using mercury. That is affordable also.
Which one?
And they are, I just talked to them, they are just sitting on the road.
See, in India, there is a lot of people who say that I can convert A to B.
Because in ancient times we don't have any resources.
See, we are talking about, that's why we are talking about science.
Sir,
Either before chemistry has become ever a science subject, that's why we used the word alchemy. The alchemist's role is to convert everything into gold. That is the motive with which they have done all the studies. But when they carried out the studies, sometimes it got confused. You understand? And it created a lot of ideas about, okay, you mix A and B and C, and there's something, there's something, what will happen. And all of them being experimented on humans. Whatever you get out of it. Okay? So even today with all the development, so people can, a lot of people asked about before also the questions of and all that. We have to look at it whether how far is it realistically possible. What is the pros and cons? Is there a science there which we are aware at that point and today we are not able to do it? Okay? That's why all these questions are left hanging. So unless it is scientifically verifiable today, you cannot take forward an idea. Okay? And if somebody is saying that, some years back, they are very young, maybe 30 years back or something like that, or even 20 years back, there was a guy who said that I'm going to make from leaves a petrol. Okay? And what he did, he showed everywhere. A lot of people are there, a lot of scientists were there, oh, guys, petrol is coming. Before they analyzed the experiment, we found that the amount of petrol is always constant. Irrespective of whatever the starting material. Then they found that you actually put the petrol inside the food. No exaggeration. I'm not talking about it because he's the guy who even went to the president's bungalow when Abdul Kalam was the president. Okay? To show that. Then Abdul Kalam was impressed and then he called the other guy, check it carefully. I want to check it. Then they found that no. So what I'm trying to tell you, it's very easy to deceive somebody that I don't convert it to be. Scientifically, no.
As an Indian woman, we are the world of war. We don't have any resources like mine.
See, there is a separation between mythology, story, and reality. That's why I said, any one of the things what you find, I find something today, to verify by at least 15, 20 different experiments, to say that yes, this is what happened. Otherwise, it will not be accepted. So similarly, all these, we study a lot of stories and it's very good at that point to create an imagination for ourselves, but is it scientifically whether we can prove all the points? It's not possible. So coming back to that, okay, Volta did the battery and they wanted to do what to do with that, and it was Humphrey Davy. Davy has two important contributions. One is, he looked at and then took the Volta's pipe and started heating every other chemical compound he is aware of. And then melting it to two electrodes and see what would happen. And then he found that he produced a large number of elements. So, if you look at, as I mentioned some time back, Glenn Seaborg produced something like 13 new transuranium elements. All of them are radioactive and unstable. And whereas Davy produced, using the voltaic coil, by hydrolyzing the molten metal salt, created many of the new elements. And he also was, like we have Vijayaraghvan today in the morning, so Vijayaraghvan served as the scientific advisor to the government. Humphrey Davy was the scientific advisor to the government in the UK. He was serving as a scientific advisor. So, what is the role in those days of a scientific advisor? A common man, common man says, I have this problem, can I not do something about it? What was the problem there in those days? The main problem in UK in those days was everything has to come from coal. Okay? So when you are looking at coal, the coal has to be mined. And when you are looking at a coal mine, whenever you are trying to remove coal, along with that there will be pocket of methane gas. So when you have a methane gas, how do you go underground? In those days, there is no electricity or anything, so you have to carry a torch. Torch means giving a fire, not a torch like what we use today. It's a fire. So you carry it down and you catch hold of a methane block, so boom, there is an explosion because methane easily catches fire. And when it catches fire, the whole mine collapses. And people who are there already 10, 20, 30 dies right there. There's no way they can escape. So these people came and then reported that Mr. Davy, we have a problem in addressing. So what he did was, he created one of the probably the most elegant approaches for a scientific problem. What he did was, you have this lamp, and then he just covered the lamp with a simple iron gauze. Okay? Iron gauze means gauze is something which is a fine mesh iron. So what is the role? Because when the burning is inside, the iron around it becomes hot. When the iron becomes very hot, when the methane gas has to come inside to catch the flame before it actually catches the iron core, which is very hot. The iron catalyzes the decomposition of methane into CO2. So with the result that methane does not have an opportunity to reach the flame so that it avoids any of those major burning, saving a large number of people during the calamity in Britain. But I put here in red, what is he himself, Davy himself considered his greatest discovery. Anybody? He never mentions any of his scientific discovery, whether it is 7, 8 element of a periodic table or the safety lamp or any of those. He never considered that as the greatest discovery. He considered discovering Michael Faraday. Michael Faraday was a fifth child and very difficult to live. He took up an employment as a book binder's assistant in London. And the Faraday was very interested to learn. So any book which comes for binding, he reads before starting the binding job. And the binder, the owner of that, got an invitation to attend Humphrey Davy's lecture. And he thought there was a young guy who appears to be extremely interested in learning and reading. He said, Mr. Faraday, why don't you go and attend these 5 lectures given by Humphrey Davy for the public? And Faraday takes it and then goes and attends. Normally, like here, come, lesson, attend lecture, etc. The same thing, Michael Faraday takes note of every word told by Humphrey Davy. And he's a binder. He comes back, binds everything, and make it into a 5-volume, and then write to Humphrey Davy that I would like to meet you. And then Humphrey Davy said, okay, you come. So he comes, shows all that. He said, what are you doing? He said, I'm a binder's man. Why are you wasting your time? Give me assistant. So he, looking at the enthusiasm of Michael Faraday, not formally educated, but gave him an opportunity to work along with Humphrey Davy. And if you look at, in terms of any chemistry you take up to this point, okay, as we are talking about the scientific development of chemistry, probably the greatest ever chemist living in the world, Michael Faraday. Okay, so because he contributed electromagnetic, you look at all the everything is, if Faraday is not there, you don't have it. Okay, and Faraday is the one who, because showed by induction. Okay, and of course I have a video on that. I will put it up here. And it is more modern. And this is the original of the Michael Faraday's induction. And say that how inductively current can be generated. Okay? And more importantly, till about 30, 40 years back, nobody worried about the idea of nanomaterial. Okay? People never thought that, one word has to be given. But if you look at Michael Faraday, called it as a divided matter. He took sodium tetrafluoroaurate and then a solution of phosphorus and carbon sulfide reduces the sodium tetrafluoroaurate into gold, and then he diluted the solution and he called it as a divided matter. Okay? And this is the bottle where it was stored when Michael Faraday made it in those years, somewhere around 1830, 1840. And it was kept even today, and then they analyzed it after people started talking about nanomaterial in the late 80s and early 90s. They found that those divided metals are still being stable up to that point, even after 150 years. And of course, the other contributions of Michael Faraday is addition to the other effects I have mentioned on the induction or the dynamo effect, as well as the material, if you look at liquefaction of chlorine, isolation of benzene for dynamo, and magneto-optical effect. Light can be polarized because it is very well used today to identify circular dichroism. Okay? And diamagnetism in compound. To me, he probably would be the greatest experimental chemist ever. So then comes John Dalton. And if you look at John Dalton, and everybody has told about the Dalton atomic theory. Okay? So he talked about all matter consists of tiny particles known as atoms. And for him, atoms are indestructible and unchangeable, and today we know that it is destructible. And elements are characterized with the mass of the atom. When elements react, they combine simple and whole ratio. Okay? Appears to be simple, but what is more important is John Dalton has other ideas about the science, not just about chemistry. What we talked about, the atomic theory, is probably one of the most important contributions in chemistry. But he also had an idea that he is not able to see green color. He believed that his eyes are not sensitive to the green color, and this is the foresight of a man. He said that preserve my eyes, keep it, and then when somebody in future they can analyze it and find why I am not able to see green color. Okay? And you see here, his eyes were removed on his request and were analyzed in 1990. Okay? And the DNA revealed that his eyes lacked the pigment to sensitize to the green color. Then, of course, we concentrated majority of the scientists in chemistry based on England. But if you look at, we talked about Volta, Galvani, etc. And at the same time, we also have to realize that Germany was another school which is also important. You need to realize that we also need to worry about the, when I mentioned the French, the Lavoisier. So Frederick Wöhler. Okay, I get another 5 minutes or something. So Frederick Wöhler, known for his synthesis of urea. Why Wöhler's synthesis of urea is very important? So, the compound which contains a carbon which come from, not from a natural source. Okay? So, of course, the urea becomes very, very important later. Very good. Then, the another one which is important is, if you look at, is a Wöhler who actually first time showed that you can isolate aluminum. Because every time, whether Davy or anybody else, they were using the same fixed idea that you melt something and then put an electrode, you should be able to isolate aluminum, and it was never possible. Whereas he used a very simple chemical approach where he takes aluminum chloride, reacts with potassium to get aluminum powder. The potassium chloride will immediately dissolve in water. Because I'll probably skip a few here about periodic table. Just because today is here with experiments, I just wanted to tell accidental discoveries. See, not all studies are scientific, methodical, or in terms of looking at the product. There are reactions which are known where people carry out and then find that they are useful. What we call it that serendipitous discovery or accidental discovery. So one is of course the Louis Pasteur who resolved the chirality in organic molecule for the first time to show that organic molecule can have R and S form. And I would tell another story which is again very accidental. discovering the purple dye, William Perkin. See, William Perkin's case is a very interesting case because William Perkin got an admission to go for a BA program or BS program to do his undergraduate education in chemistry. And finished his school, he had few months for free. So he went and then taught and then wanted to experiment some studies in chemistry before he can do something. So what he did was Perkin go and meet a professor and then say that I have 3 months time, I am working in a lab. The professor at that point said, no, I am very busy, I am going for a Euro trip. My lab assistant is there, he will help you. Your job is to make quinine. Because quinine is something which people use for treatment of malaria. So he wanted him to look for a synthetic methodology to study quinine. But the starting material they had was aniline. So they had only aniline, and he said that he use aniline and carry out the reaction. Of course, he gave some methodology which didn't work. Eventually, it formed with some kind of a very dark colored compound, which on washing, when the whole experimental setup broke and he wiped into the cloth is not this. And then it finds next day that the cloth has turned into a deep purple. He doesn't know what to do, repeat the experiment, find the same thing again. And he called it wow. Of course, he applied for a patent. He was successful and he sold his company in 1874 and retired. So that roughly around 30 years he worked, basically. And then he retired, or even less. Okay? And if you look at the quinine atomic synthesis, the radium pyridine with oxygen with potassium dichromate, you should be able to produce quinine. But when you do the experiment, the aniline gets converted into the wow or the pink color or purple color. Okay? That's the original patent. So next one is, so you take a test tube of concentrated sulfuric acid and then you add concentrated nitric acid in that. Of course, the mixing of both sulfuric acid and nitric acid is going to create an extremely hot solution. Then you put words of cotton inside. And then you neutralize the whole thing with sodium bicarbonate and then you remove it. That cotton now is soaked with nitrocellulose. Okay? And the nitrocellulose is a very important thing because nitrocellulose catches fire very quickly. Okay? Till Albert Noble comes up with that, they were using nitroglycerin. Any of the, if you want to make a rock, if you want to kill a person, everything was used to form a set of nitroglycerin, which is extremely sensitive. Whereas they were using cellulose nitrate with a mixture of ether alcohol to patch any of the wound during the war or any accidental injury. Then he decided that I am going to combine the collodion with the nitroglycerin and then it forms a gel, he called it gelatin. According to patented it, became very rich and then he also created how to detonate it. Then he also developed dynamite. The Nobel Prize, which is the most important prize in any improvement of mankind, the money for that, please remember that comes from the World Wars and especially World War I during the time and mainly by generating the kind of the bombs created by the Alfred Nobel. The another one which may not be that obvious is that Röntgen discovery of X-rays. See, when you are looking at the study, Röntgen was studying a cathode ray. Now we are already looking at close to the beginning of the 19th century, 20th century. So when you are looking at the Ramjan was wanted to study cathode rays, whether they could escape a glass tube like here, and then it can come out of it in a dark box containing material. But he observed that in a darkened laboratory several feet away, there was some kind of a glow. He named the penetrated rays as X-rays because, like any unknown quantity, because he doesn't know why the light is coming up, you always mark it with X. It so happened that that word actually stayed. Okay? Even today we call it X-rays. And normally in X-rays, what normally you do is you have a tungsten filament which you are basically heating, and by applying a very high voltage, then what happens, the external electrons are ejected from the tungsten filament, and then they hit the anode. The anode is normally copper, you can also use any element of the periodic table. Then the idea is, you know that various orbitals which are surrounding the nucleus, and if you look at the K shell, the L shell, the M shell, etc., you specifically knock down the K shell electron, then the M shell electron immediately come and then occupy that. That energy different is what comes out as the X-rays today. And I think it's the last one, but I have a lot of other experiments that was going to show here. Yes.
Previous slide, what was the meaning of like those penetrated rays?
You know, I think penetrated rays. See?
Name the penetrated rays.
See, what happens is, see, if you have these, same thing, when you are looking at a cathode ray. So you have a cathode ray. Okay? So when you are applying, by that time, Faraday has come. Electricity has come. So people know about electricity, voltages, etc. So when you are applying to that, what he thought is you go to generate rays. And what will be the penetration depth for any of those things? That's what we are trying to study. Will that rays which comes out of the cathodes will have sufficient energy to penetrate? So if you look at these X-rays, how much do you think will have the penetration? So, it can penetrate some. Okay? Because the X-ray what is being used in the laboratory, the X-ray what is being used in a hospital are very different. Okay? In terms of their overall energy. The same energy what you use in a laboratory X-ray, if you use in a hospital X-ray, what you will be energy here. Okay? So the amount is here, basically as I mentioned that you have to knock out a K shell electron so that the M shell electron will jump in. The energy difference between those two are something X-ray is a characteristic wavelength. Because you are looking at M to L energy difference. Okay? So that would be a characteristic energy difference. Okay? That's why if you read anywhere, they put it as a K alpha line. K alpha line. Whereas if you use the lower energy, it will not be in a position to knock out the K shell electron, but will knock out some other electron outside. Again, the same jump will happen, but that will not be a characteristic one. So that is what we use, the very mild X-rays, what we use. Again, if you look at, it penetrates the tissue, but it gets stopped in the bone. Understand? Because the bone, that's why you are able to see the bone. Okay? So, any of the time, they look at, depending on the energy what you give for these thermal electrons. So that means that you are looking at how much voltage you are doing it here. We are normally give 40 kilovolt. That is normal voltage in laboratory X-ray. Where the kind of voltage what they use in the laboratory X-ray varies between 5 and 50 kilovolts. So it will be even much lower in the X-ray what comes out.
So the X-ray energy depends upon how much voltage are we giving or upon the metal which is emitting it.
Always the energy. The thing is, this is the most important thing. These are the external electron coming out of the tungsten filament. element is the one when you are applying the high voltage, it's switched on. And then the external electron gets knocked out. So it keeps moving away. So you focus it, you hit on an arrow. So those electrons, the speed of it and the number of it depends on how much voltage you are going to use here. That means that you have to give the everything is under sealed condition. It's a modern tube. Everything is sealed under vacuum. So it's not external. Okay. So these, when it is sealed, how much it can heat up. That's the thing. So how further you have to do, you have
So X-rays are not visible to the naked eye. And when Sir William Vernon explained the experiment, how can he detect the glow in the dark room?
voltage. The problem here is the voltage. If we are now talking about very high voltages, that in those days the voltages was very limited because the current started, or electricity started being produced at that point in the cathode rays. Okay, so everything depends on the amount of energy what you do. Okay, that's what I said. You have to look at it and go back into 1896 when he was observing 100 years back. Okay, so that current itself is many places over here.
I am not asking that. Our eyes cannot detect X-rays. We can only detect visible rays.
Like I said, 10 kilovolt, where do you go for 10 kilovolt? To get a particular electron on top. The cathode ray, where are the cathode rays? See, cathode ray, in old days, you have a huge TV. This kind of big TV. Now everything is tiny. And my idea is mechanical everything is different. Big TV. What do they have? They have a cathode ray in the back. Okay? And what the cathode rays send out? Same thing. So you put an electrical pulse, and then you take the ray comes out of it, and you have what we call it a sensitizer in that. The sensitizer will have a specific element, mostly direct element, so that you can get excited to the higher excitation wavelength, and then give out a specific wavelength when they come out. Luminescence. That is what it is all used in all those things. That is what the cathode ray normally does. Okay? And based on that, people identify this as a because there is limited. The same thing, if you go back and look at Madame Curie, she also discovered something which comes from radioactivity, radium. And then she isolated radium and kept it. And then she was searching something at the bottom, it's at the top of the table, and she was searching it in the drawer under the table by her hand. Unfortunately, there was a photographic film around it. She didn't know that, so she kept it. And then when she woke, oh my God, let us check it, what happened. So she went and looked at it, and then she found all the things, including the ring. You won't read the Madame Curie's. So each one of them at that point, they are not aware what they are going to look for. They are seeing that if the cathode ray will come, how much the cathode ray can penetrate and see anything. That's what it is. We don't know when he talked about the laboratory, we don't know what it contains. Assuming the laboratory contains some ordinary what we use it as a paint. Okay, even if that has to have some painting. What, even older days, maybe calcium hydroxide, calcium carbonate. So see whether that flow, because the ray can hit and then that can be erased. Okay? It's truly that. The last one, and 1 minute and 30 seconds more, I'll take 61. So, Teflon. Why I am talking about that? Teflon is all over the place today. People don't want to look at Teflon because suddenly they find that Teflon is bad. Perhaps non-stick. Okay? What actually did was, Plunkett was asked to look for, in those days, in DuPont laboratory, that to look for a newer refrigerant because they thought that carbon compounds are responsible for, in those days, so-called what we talk about the global warming, etc. what one is better. So he isolated the molecule, tetrafluoroethylene, and put it in an iron container. And that he did a day before Easter. He left it as okay, I'll come back and study the refrigerant property of this tetrafluoroethylene. And he goes back and comes back on Monday, he finds that there is no gas coming out of it, but it's still heavy in the gas cylinder what he has left it, because tetrafluoroethylene is a gas. You see here, and he had an idea that maybe there is something else there, and then he cuts open in the laboratory and finds that the whole thing is a white mass. What actually happened was, this is made of iron, that gas cylinder, that catalyzed the tetrafluoroethylene into polytetrafluoroethylene. And of course, the continuing story on that was, he found also that the polytetrafluoroethylene is not soluble in any known solvent. It is not soluble in any solvent. Okay? It is not soluble in any solvent, not attacked by any acid, not attacked by any base. So he actually kept it for a long time, 5-6 years, without ever doing it. And before that, they identified how they can modify it, make it many other things. And today, everything depends on electrons. Okay? Of course, it has a lot of other scientific uses rather than one non-stick value. Okay? And I will probably stop it here at a lot of chemical reactions which I want to show, but I'm sure that the masters here will be able to an expert on chemical reactions, and he will explain you and explain you with that. Okay? I will kind of stop it here. As I said that, I kind of, if you are looking at the time, I kind of stopped the metal periodic table, which is possibly the birth of modern chemistry. Okay? Up to that point, if you look at, all of them are trying to identify different areas, and of course, once you have the modern periodic table, then you look at J.J. Thomson's experiment, and then they go further, and it becomes more developed science. Okay? Thank you very much, and if you have any questions, I will be happy to answer.
So you talked about the thing which was formed. Can you repeat the name, which was not soluble in any known solvent? What was the name of that product formed? So was it polar or non-polar?
You can use anything even today.
So that
Teflon is one material you cannot use it. Is it polar solvent, non-polar? I told you all acids, all bases, all non-organic solvents. Nothing with it. Teflon, he kept it for 5-6 years without doing anything. It was done in 1960. 1966, 67, they kept it. Before they again started, let's look at it and see whether how we can do something about it. So that's how they basically manipulate it, then refunctionalize something, so that we can coat it and make it other things.
Sir, can we use noble gases as catalyst in all liquid reactions? Noble gases as catalyst.
Yeah.
In all liquid reactions.
See, thing is, when the reaction is sluggish, when the reaction is slow, or the product formation is limited, then you look for a catalyst to speed up. And then the catalyst, what is the role of the catalyst? Catalyst need to form an intermediate. The so-called reaction intermediate has to react with the catalyst to form an whole thing of intermediate. Unless you have that, because if the catalyst is there, it doesn't form proper intermediate, you are not going to form. Look, the whole idea is if you look at your energy curve, the activation energy value has to come down. That's one of the rules. And when the activation energy comes down, then automatically what you look at from the left side to the right side, the product side, concentrating into reducing the activation. So reactivity improves. So that is the reason why you need to not necessarily that all reactions need to have a catalyst. But there are reactions that you have to look at how fast it is, what is the kind of product you get, then you go back and do that. That's the question, isn't it? Huh? Tell me. No, it doesn't. Huh? Huh? No, nobody is not reacting to them.
They are also not involved in reaction.
If you look at the local gases, you look at helium, okay? Any one of those gases, they are ocean. Making a reaction out of it is almost impossible. Understand? Whereas if you are looking at any of these noble metals is not lack of reactivity. Not electrons can be exchanged. So platinum can go to platinum 2, platinum 4. Gold can go to gold 1 and gold 3. Very easily. It's not a problem. Same with sodium. Same with helium. Understand? So we are looking at in one side what we call it a transitional element. A transitional element, if you look at anything you think of, you can do with transitional elements. Okay? The 10 element, whether 3D10, 4D10, 5D10. If you leave that, chemistry is not there anymore. Understand? The entire chemistry, development of chemistry depends on these 30 elements. And there is, you can add 14 or else after that. So everything else on either side of it is okay. Main thing is transition. So if you are looking at any one of the noble metals, you are all transition. So that reactivity is there. Not that you can always form like I told you, when you are looking at Faraday forming that gold nanoparticle, he has to start with the compound. It's not like he started with the gold metal and start 100. No. Understand? So therefore, that if you are looking at the noble gases, the number of helium has few. If you look at all of them, very difficult. They are if you look at the kind of interaction what we look at. So how do we look at any interaction between two species? Any two species. You are looking at some kind of bonding. So you have talked about ionic bonding, you know about covalent bonding, you know about coordinate bonding. If you are looking at a metal, you are looking at a metallic bonding. And if you are looking at any bonding, when you are looking at noble gases, van der Waals interaction. Van der Waals interaction is very deep. Even if you want to isolate, not want to stay together. That is why even if you look at it, very, very difficult, you decompose some of them. Okay, so that reaction is very good. So you can't use any of them.
Is Teflon a solid?
Yeah. So, don't worry.
Yeah, so earlier we were talking about how Glenn Seaborg managed to convert lead into gold through nuclear reaction. You mentioned that's very energy inefficient, so it probably never be used to commercially produce gold. Do you think there will be ever a point in the future where using nuclear reactions to convert one element into the other would be viable, or at least the preferred way for anything?
What is the drawbacks of any of those reactions? The drawback of all those reactions is whenever you are using anything to do with nuclear and nuclear related things, the product what you are going to get is hot. That means it is going to emit always a gamma radiation. Not only gamma but many other radiation. We are looking at X-rays and very weak X-rays. You look at how I told you lab X-ray, you expose it, you are dead. I'm not exaggerating. By the time you are looking at gamma rays, it is even more powerful. See, you are looking at 1 kilo electron volt is the kind of energy for X-ray. 1 to 10. 100 mega electron volt is the energy for gamma rays. Just measure the level. Okay, so many of the nuclear reactions, even the product come, they have been hot for a long time, the half-life period, they are worried about all that. So it's not going to be of any use.
You
in the miner's lab, sir, you told iron acts as a catalyst when methane, when it is going towards the flame. So what is the final product, sir? Does it form CO2? And yes, my second question is about like the galvanic cells. Like, was Volta's reference galvanic experiment, and based on that he designed his batteries. So like, what was the main difference between galvanic cell and Volta's cells?
If you look at a galvanic cell, the galvanic cell is an idea based on two, when the idea is when you are looking at two dissimilar elements, you touch it, that will be a flow. That's it. To prove that, you have to do that. That's what Volta has done. He said it's not just the two dissimilar elements, you touch it, the flow of electricity, you also need something called electrolyte. So that it will be sustainable. You understand? So you put this and it stops. You move it, everything stops. The galvanic cell. Whereas in the Volta cell, once you construct it, it will be working till it sustain all the energies consumed. That's it.
So I mean, like standard hydrogen electrodes, sir. Like we use like electrolyte acid, which is based on hydrogen, and we pump in hydrogen gas through platinum catalyst, sir. So how does it produce that zero potential, sir? We take it as a reference for all other electrodes.
See, for everything you need a reference. So whatever you do, even when you get a mark, there is a reference to that. See, even if you take a percentile, there is a reference to that. Similarly, whatever the thing you take as a reference, then based on that, you arrange all of them. So normally, when you are looking at periodic table, isotope, in those days, the isotope was based on carbon. Carbon 13 was an isotope to arrange all your isotopes in periodic table. Similarly, we need a reference. That's what the reference.
Like hydrogen, standard hydrogen.
You have to have a hydrogen electrode, you have hydrogen. There is something called a platinum electrode. So, the platinum will be a reference. There are many electrodes are there. So, each one of them has different references.
Thank you, sir.
One last.
Sir, how Teflon is injurious for health?
How?
Teflon is poisonous to health.
Poisonous. See, the thing is, Teflon is polymer, that is polytetrafluoride. Okay? So, polymer. And when you are looking at, you are consuming in a non-stick which contains Teflon. What happens after some time? You get microplastics go into the system. You don't know what's going to be the effect of it. And people have not identified the cause of why the major problem today. What is the major cause of death today? Cancer. Across the globe, I'm not talking about India, China, or America. Across the globe, the maximum population. We don't know yet. Because still there are not things, there are not anything yet. Because the system, it gets deposited. We don't know what which it triggers. They are not identified yet. So it says, okay, let's go back. Previously it used to only iron, pure iron. You know that people survive.
Any more questions?
Sir, to flow current between zinc and copper, sir, in that experiment, sir, we use leather between them.
That he used. As I told you that today you can go to a market, buy the zinc ring, very easy, and then copper. You can go to any of those, here I can tell you that, but other places I don't know where you can go. You can get the washers, metal washers. So you go to the hardware store and ask for zinc washer and copper washer. Just take it, cut a newspaper, I told you, make a sodium chloride solution. Preferably saturated solution. Same size. Aluminum foil, you have to put the aluminum foil, put one first, metal, put this copper, put the paper, soaked in sodium chloride, put zinc, then put copper on top. So boron assembled, each one on cell at 6 cell.
Any more? So I would like to thank Professor S. Natarajan for his lecture, and I think we have got.
Okay, thank you.
I think. So I would like to call Shikha for introducing Professor Uday Mitra.
If you are planning for a year, sow rice. If you are planning for a decade, plant trees. If you are planning for a lifetime, educate people and research. One of the greatest examples is Professor Uday Mitra. Professor Uday Mitra is an Indian organic chemist and a professor in the Department of Organic Chemistry at IISc. He was born in Durgapur, West Bengal. He has done BSc in Presidency College in Chemistry. He is known for his interest in studies on molecular tools and supramolecular assemblies. He did his MSc in IIT Kanpur and his PhD in Columbia University, New York, along with Professor Ronald Brestock. He even did his postdoctoral research associate. Not only supramolecular assemblies, he is also interested in photoluminescent metallurgies, paper-based sensing of biomolecules, chemistry of bioacids. Due to his awesome research work in chemical science, he is recipient of the Santi Swarup Bhatnagar Prize for Science and Technology, one of the highest Indian science awards. Hope that we will enjoy his session, and so I welcome you to this lecture.
Thank you.
introduction, and also thank the organizers, that is IISc and the Agastya Foundation, to put together this program. Professor Natarajan was not able to talk much about the periodic table. Yeah, so that's why, I don't like wearing ties. So do you notice something interesting about my tie? It's a periodic table. So I start with the periodic table. Okay? Now, periodic table itself is not chemistry. Okay? Because chemistry will happen only if bonds are formed and bonds are broken. So the periodic table, while it lists now how many elements? 118, right? But periodic table is about chemistry, but unless atoms form bonds or unless molecules break bonds, there is no chemistry. Okay? That's the fundamental thing we need to know about. Now let me go back and get my presentation started. Now we are starting very late. So, how hungry are you? You are hungry. Okay, so am I. So what time shall I finish? Because I was given two 60-minute sessions, which is total of 120 minutes. I set my timer to 120. So how do we proceed? I can stop anytime, either temporarily or permanently. Okay, so let me know what time I should stop for lunch. 1:30? Okay, so in that case, we have 37 minutes. Okay, I'm very particular about time, so I will stop at 1:30 or until the closest experiment gets over. Okay, all right? And then we will come back hopefully by 2:15 so that things don't get delayed, because I will need an additional 60 minus 37 minutes to finish my talk. So I'll start my timer here. No, I cannot. One second. Let me pause. I need to test the audio as well. Audio? Headphones. Audio? Headphone audio? Not going. Let me try display audio. But that is only there. It's not in the, I think that's okay, good enough. Okay, let me try again. I'm not going to play song or music, okay? Except there will be a song and you can dance at the very end with the tune. Okay, so I think the audio is sort of okay. Let me make sure that the slides go fine. Okay. Test slide is okay. So let me restart my timer. All right. All right, okay. So this was, this is actually meant for younger kids, all right? Not for you. Before I begin, I would like to thank my team members. Please come to the front so that I can introduce you. Gaurav, Nandita, Simpa, Arindam, and Louis. Let me thank all of them for the help with setting things up and also help during the experiments. All of them are from IISc, all of them are working at IISc, but Louis is an intern from Sorbonne University in Paris. So thank you all for the time you have spent in putting things together. Thank you, you can go back. I should also thank Dr. Palani from Merck, because I use a variety of chemicals for this purpose, and some of the more expensive ones are supported by Dr. Palani, and that's why I will be able to show some of those to you. Is anybody's birthday today? May 20th? No, that's why we have some balloons here. Okay, all right. But then every day of the year, and we have an extra day this year, right? is very important in the history of science and history of chemistry. So let's see what all has happened on this day, that is May 20th. Have you ever seen or heard about a Buchner funnel? Buchner funnel? Maybe not, okay? But Edward Buchner was born in 1860. He discovered alcoholic fermentation without yeast, okay? We don't want to get into the details, but he also invented the Buchner funnel that you will be using in the lab sometime soon. Got the Nobel Prize in one of the early years, 1907. Erika Kramer was born in 1900, and she put out the theory and development of gas chromatography. Have you heard about gas chromatography, GC? We will have another occasion to highlight the importance of gas chromatography. James Lind began a very interesting experiment on vitamin C, on sailors. You might have heard this story. So he was born, his year of birth is not shown here, but I think he started this experiment in 1847. And last but not the least, Hans Meerwin was born on this day in 1879. Normally oxygen has two valency. But in principle, you can make a trivalent oxygen compound called oxonium species. So two methyl groups attached to oxygen is called dimethyl ether. But he was the first one to put together a third methyl group. In that case, the oxygen becomes plus. So that is called trimethyl oxonium salt, and that is frequently called Meerwin's reagent. Okay? To celebrate the importance of May 20th, we will do a small experiment. Can I ask the first row to just temporarily go to the back side? No, this is only one. We'll do only one. For doing any chemical experiment, you need to be careful, extra careful. I've done this experiment hundreds of times, no issues. But since it's a closed room, you should know that there is an exit here, there's an exit there. Okay? Anything goes wrong, just run. We do have a fire extinguisher, and wait, hold it. We also have a fire extinguisher in case something goes wrong. Now, this is a balloon which is floating. Let me start with a question. Why is it floating? Inside is helium. Hydrogen. Any third choice? Third possibility? No, specific gas. Hydrogen is a possibility. Helium is a possibility. Third one? Argon is heavier than air. So it has to be lighter than air. Right? Air has a density of 14.4, relative density. Okay, it has to be lighter than air. Methane, molecular weight is 16, relative density is 8. Okay, it's much heavier than hydrogen or helium, but nevertheless, let's say it's not methane, it's either hydrogen or helium. How do I find out? By popping it with fire, not with a pin. Okay, then both will pop out, right? So let's see whether this experiment works. I will also I think this balloon is too small, so it will only make a pop, small fireball. Okay, shall we? This balloon has a capacity of 2.2 liters. Okay, keep that in mind. I will give you a problem with that. No problem. Thank you. Okay, so you saw the reason I popped a hydrogen balloon here is because Bangalore is suffering from water shortage. So we made a little bit of water here. Okay? So, but then there's a question. How much liquid water did we get out of this balloon if the volume was about 2.2 liter? Okay? You think about it and you said, tell me the answer later on. It's very important in science and perhaps in other subjects also to be able to ask questions. This is something that was discussed during the inauguration, right? So it's very important to be able to ask questions. Those who have gone back on the rear bench, you can come back to your place. Let me illustrate this thing with this picture. He's a very famous scientist. I will reveal the name in a bit. He said, remember when you were young, maybe going to elementary school, you come back home, and whoever is at home, maybe your grandparents, maybe your mother, if she was not working, what would they typically ask? How was your school? How did you do? And so on. He said, not my mother. My mother would ask me, did you ask a good question today? Okay? And then he goes on to say that difference, asking good questions, made him become a scientist. And who is he? He was I.I. Rabi. He got the Nobel Prize in Physics in 1944 for discovering the resonance method for recording magnetic properties of atomic nuclei. You may not have heard the exact technical term, but I will highlight 3 keywords. What technique is this? It is discovered by a physicist, extensively used by chemists, still being used, and now it has gone to medical doctors, MRI. So it is called nuclear magnetic resonance. And Louis comes from France, and they call it RMN in the way it is written here. So I will also keep asking you questions. Have you heard about Occam's razor? No. He was an English clergyman, I think in the 13th or 14th century. Okay, this is not about asking questions, this is about answering questions. Okay, what he said is very interesting, that all things being equal, the simplest solution tends to be the best one. Okay, or in other words, when faced with 2 possible explanations, the simpler of the 2 is the one that is most likely to be true. Okay? So this is something that you need to keep in mind when you're answering questions. One of my college teachers also said that you should remember ABC. Easy to remember, right? Your answer should be accurate, brief, and clear. Okay? And that, along with Occam's razor, actually solves all the problem for you. Sorry? Good question. I'm not very sure. But you can look up the Wikipedia. I think there is some explanation which I did not completely understand. Okay? I'm digressing a little bit because this term came when Professor Vijay Raghavan was speaking. Because we all know that we have polluted the atmosphere and the earth to a place where it is no longer reversible. The current heat wave all over India is a good, sort of good example for that. If you think about Earth in the solar system, Earth gets nothing from outside, no material other than sun's light and cosmic rays and things like that, solar storms once in a while. Nothing goes out of the Earth. Nothing. No material, no gas. Okay? And therefore, we are in a very difficult situation with the increase in population. Every process that we can think of, all human processes require energy and increase what is called entropy or the disordered state. We take ores from concentrated deposits and dilute them. Okay? And for example, this mobile phone has about 46 elements. Okay? We are using it, throwing it away, and not recovering much of that, although the situation is changing. So you need to be careful. And if you think about reduce, reuse, recycle, which all of you know, I assume, the first 2 R's do not require any energy, but recycling does require energy. We talk about solar energy, but the solar panels have a lifetime of the order of 15 years or 30 years, depending upon the quality. And in about 10 to 20 years from now, things are going to be very, very difficult because we have generated several hundred square kilometers of these panels. Where will they go? Unless you recycle. If you want to recycle, it will cost a lot of energy. And that technology is not yet developed. Okay? And your generation has to be absolutely careful about reducing and reusing things, because recycling is expensive in many cases. So the bottom line is reduce the waste generation. I think Professor Vijayaraghavan also talked about sustainable development goals. So the United Nations had put together 17 of these SDGs. 2022 was initially called the International Year of Basic Sciences for Sustainable Development. Now it has been changed to the Decade of Sciences for Sustainable Development. And there are many which concern us, and today we are probably talking about quality education, SDG 4, in this particular program in a limited way, although we are touching upon many other things. So keep this in mind and get more information from this as we come along. All right, with this long introduction, let me talk to you about chemistry is fun. You are all 11th grade students? 12. Oh, that means that I cannot skip one experiment. This experiment will have to be done. So you have just started 12. Excellent, excellent. So all experiments will be done, and we have 106 minutes. Okay. Let me ask you a question. Shall I ask you a question? This is a difficult question for you to answer. Okay? Don't worry about what your teachers would think or what others will think. How many of you dislike chemistry? Raise your hand. Yeah, how many of you do not like? Others are very hesitant. I once had about 100,000 students, close to 800,000 students, and almost everybody raised their hand. You are very shy. You don't want to be caught in a controversy. Okay. But chemistry is really fun. Okay? And hopefully, in the remaining time that I have, I will show you how chemistry can be fun. I will not cover a lot of chemistry like what Professor Natarajan did, but I would like to touch upon various things and show you that chemistry can be a great deal of fun. And as I promised, there will be a song at the end relevant to our discussion. And then, of course, feel free to dance. Okay, nobody will object here. Something is everywhere. What is everywhere? Chemistry. Let's put the words together. Indeed, chemistry is everywhere. It's very close, is as close to you as the supermarket. Okay, and I'll show you something from the supermarket. And for legal reasons, I will not show the brand names, because somebody may say that, why did you say certain things about my brand? This is the package from a commercial bread. I hope that when you buy a food item, commercial package, what is the first thing you look at? Expiry date. Second and the third things that you should look at is the nutritional information and the ingredients. If you look at the ingredients, for example, this was a multi-grain bread. Okay, you see these, let me just put, this is better. You see some numbers, 3-digit or a 4-digit number. What do these numbers mean? These are approved food additives that almost every commercial product uses. They're not necessarily bad, but you should know what they are because you're all science students. Because these are given not just for the students, but from the general public. So the public should have an awareness of what these numbers are. What are they eating along with their food? And if anybody has an allergy, then he or she should avoid that. Let me list out some of these. And these are called, earlier these were called E numbers, European numbers, but now these are, labeling is different. It's called INS or International Numbering System. These numbers I have indicated. 212, for example, is calcium propionate. These two are ammonium chloride amylase, acetic acid, calcium phosphate, mono and diglycerides, ascorbic acid, which is also vitamin C. Remember, we talked about vitamin C in one of the early slides. This is about bread, but everything you can think of from the market has certain additives built into it. For instance, this is a very hot summer, so many of you probably are drinking buttermilk. This is again a commercial buttermilk, okay? And I've got the numbers. I think there is only one additive that is listed here, and that is microcrystalline cellulose, okay? Now, the other thing is that when you look at these numbers, percent RDA, let me go back to the Zoom, okay? That is recommended dietary allowance. That means this 200 milliliter package gives you 3% of your daily requirement of energy, which is roughly 2,000 calories for an adult. But does something surprise you here? 0% is, there is no sugar added. Blank means nothing is there. Protein means there is no protein, no added sugar, no cholesterol, no trans fat. But anything else that surprises you here? Yeah, well, it gives 3 to 4% of your other dietary needs. It's got 25% of your salt requirement. Okay, 1/4. And you see, sodium content is about 500 milligrams. And these days, these companies have become clever. They don't write salt, they write sodium, because sodium has the atomic weight of 23, salt is 58 molecular weight. So if they write sodium, it looks like a smaller number, right? So 500 milligram of sodium is actually more than a gram of salt. And that much of salt you are taking in one pack. Taking one pack is okay at your age. But more than one, particularly people who are senior citizens like me, should be avoided because it has got too much salt, especially those who have blood pressure problems. Let's continue with one more product that some of you might like to drink. And that is, again, brand name removed. This is iced tea. Okay, again, this is the nutritional information. I was attracted to it because it has got only small amount of salt, sugar. Okay, added sugar is only 3.6 grams. But then when I looked closely, then I realized that it has got something else. It has got a non-calorie sugar, something that is derived from plants. And sometimes it is semi-synthetic, called steviol. Okay, there are many brand names. I don't want to mention it, but this is also has this INS-330, which is citric acid, INS-296, which is malic acid found in apples and pears, and INS-960, which is the non-calorie sugar. Okay, so again, this can actually help you understand and learn a lot of chemistry that goes in food. I have shown you only examples of food, cosmetics, medicine, and so on and so forth. I think all of you can learn a great deal of chemistry simply by reading. For example, this is a typical, the 466 was cellulose gum. It's also called sodium carboxymethyl cellulose, it's derived from cellulose. Yeah. Yeah. That's right. It is added not because of any fiber requirement, but it is to make, it is also microcrystalline cellulose is also an emulsifier. Okay, because this buttermilk basically has a fat that is suspended in water, but fat will not dissolve in water. So you need an emulsifier. So that's why microcrystalline cellulose is used in some cases. In some cases, the earlier examples, for instance, they use some glycerides, triglycerides, and so on. Yeah.
Is that GDA similar to RDA?
Which one?
The GDA per
I believe so. I don't know why they have used GDA because it should be similar to RDA, but I do not know the difference between the two. Good point. Yeah. It's a sweet, non-calorie sugar. Sugar, that is sucrose, gives you calories. 1 gram of sugar gives you how many calories? Yeah. You have studied in your middle school. Fat, carbohydrate, protein. How much calorie do you get per gram of these? It's important to know because that's how you can calculate these numbers. See, fat gives you maximum calories. 1 gram gives you 9 calories, kilocalories. They're called calories, kilocalories. Whereas a gram of protein or carbohydrate gives you 4 calories. All right? Yeah.
What is the difference between a calorie sugar and non-calorie?
Okay, both are sweet. Sugar in the sense that sugar we typically associate with the sweetness. So non-calorie sugar gives you the sweetness, but it does not get digested. So you do not get any calorie out of it. Okay, it doesn't give you more energy. Okay, but it tastes sweet. Whereas sugar will get degraded into smaller and smaller fragments. Ultimately, it will give you a lot of energy. So those who would like to limit their intake of calories, they prefer to go for low-calorie sweeteners. It is only for sweetness. For example, you might have heard about saccharin. Saccharin was used for a very long time. It is still used. Other one is called aspartame, which is a dipeptide that is also still used. But in the last few years, this stevia glycosides, okay, it comes from a stevia plant, that is now picking up. It's much more expensive, but then, you know, staying away from calories can be expensive. It does not give you calories, but it gives you the sweetness. Sorry? No, those who are diabetic, they can take this because it is not sugar. Was there a question here?
So, like diabetic patients use those sugarless tablets. So, is it better for these materials?
Those who have to control the amount of sugar, okay? Sugar means sucrose. By sugar, I mean sucrose or fructose or glucose. They can opt for an alternate non-calorie sweetener. And stevia glycoside is as close to nature as you can think about. That does not give you calories, but it gives you sweetness. I don't like this. I take coffee or tea without sugar. Okay, so one more example. This is a toothpaste. This is a toothpaste that is sold in United States called Crest. But then here again, there are many things which are listed here. Okay, and if you study these materials, chemicals, you will also find out what each of them do to your teeth. Okay, when you brush, and you can learn a great deal of chemistry with this. I'm just illustrating a few examples that chemistry is everywhere. Okay, now let's go outside Earth. Okay, and look at this picture taken by the last manned mission to the moon. Manned mission, I am not being gender biased, only men went, so I can still say manned mission. Okay, this was taken by Apollo 17, long time back. Now this is fondly called the blue marble, but we are kind of destroying it. And unless we are careful, it may one day look like this. And that's a picture of Mars. And as far as we know, Mars doesn't have water as much as we have. They may have some water. Okay, and when I say chemistry is everywhere, you know, your age group, students in your age group, you get excited by all these rockets that we send to the space to go to planets, moons, other rocks, comets, and so on. But do you know that while it takes a lot of engineering and physics to take the object out of Earth to the other place, but what is the main purpose of these missions? The main purpose is to do chemistry on another planet. Okay, you probably did not know that. For example, this is a picture that you saw a couple of years ago. Does it look familiar to you? This is the Perseverance rover being lowered on the surface of Mars. And this was the rover. I'll show you an older rover also. And if you look at all these equipments on this rover, most of them are actually used for doing chemical experiments. Because what is important in all these planetary missions is to find out the chemical composition, to find out whether life ever exists, or can it support life in the future, because we need to think beyond Earth. Okay, of course, it is very energy intensive to go there. So here is another example. This was on the American Independence Day back in 1997, and you see this, I call these things very expensive remote control cars. Okay, I'm sure that all of you like playing with remote control cars. That's liked universally by boys and girls. Okay, and this is an expensive one costing about $400 million. And what it is doing is to position a spectrometer to find the chemical composition of this rock. And it found some of these elements which are shown here. Okay, we will not go into the details. Here is a more recent picture, well, recent in the sense almost 20 years old, picture of the surface of Titan. Where is Titan? No, Saturn's moon. Okay, so this was a mission called a Cassini mission. Okay, the Cassini spacecraft circled around Saturn, took beautiful pictures, and eventually, you know, Titan has a very thick atmosphere, so nothing could be seen from Earth. So what NASA did was to have an equipment which was called Huygens probe. Huygens probe was shot onto the surface of Titan. It went through the atmosphere, recorded pictures, and this is before it crashed on the ground. This is the picture it took, okay? And what it found is that the atmosphere has methane, and there were methane lakes and methane rain. It's very cold. Methane boils at minus 183 degrees, okay? So this equipment, is, as you can see, these are all batteries all around it, okay? But in the center, there is an instrument called GCMS. We talked about gas chromatography. This is a gas chromatography mass spectrometer, because that's how it was able to analyze the atmosphere through which it was landing. So that's why I said chemistry is everywhere. Don't forget that our interest in these planetary missions is primarily to do chemistry, but it needs physics, engineering, and other disciplines to get there. Okay, here's the first question, and there is no prize for answering this. You all know this, right? This is a very old iron pillar which has not rusted. But I'm going to show you something that you have not seen, but you have studied or you are going to study. Looks very similar to the previous picture, right? This is a chemical reactor. And a chemical reactor that has played and still playing a very important role in our everyday life, because it makes life possible in some way. Okay? So think about it. I'll come back to this. Okay, I'll give you a hint as we go along. But the answer will be after lunch. So that's the question. When you see this cue, that I'm going to ask you a question, and one of my volunteers should remind me that I have asked these questions. Okay, I may lose track of time or forget it. Chemistry, now two of you need to get activated. Chemistry often looks like magic. In fact, magicians make use of chemistry and physics both, okay? And they do the magic, but they won't tell you why certain things are happening, because otherwise they will lose their job, right? So we will do many experiments which may appear to be magic, but we will explain everything, okay? Because part of my motivation for doing the experiment is to highlight to you that behind every experiment that we do, there is very interesting chemistry you have, okay? And you will learn this principle whether you know it or not. Okay, one on the right hand, one on the left hand. We are going to do a very simple experiment here. Maybe they can come above the podium so that everybody can get to see. Again, this is a very simple and safe experiment that we are going to do on magic writing. But just to illustrate the principle that safety is important, I have asked them to put on safety goggles, mask, and a glove. Please come to the to this side. Okay, so what's your name?
Abhinav.
Abhinav. Abhinav, you hold it here. You come here. What's your name? Avni. You hold it with your left hand. Hold it high and come a little bit to the front. Okay, so that everybody can see it. If I were a magician, I would say nothing is written here. But obviously something is written. Something is written. Okay, so we will try to read this. I have to come here. All right, move it up. So let me spray this liquid, okay, and see what happens. I will tell you about the chemistry part a little bit later. Okay, simple. But then one chemical, two different colors. Is it something that you know? Thank you very much. Two chemicals have been used, but then I sprayed only one. You can keep your mask because mask should not be exchanged. No. Yeah, you can remove the glove, remove the safety goggles, and go back to your place. Thank you very much for participation. Abhinav and Avani. Pavani, okay. You can stick it here if you have any tape. Okay. Nothing is written here. You know, it is absolutely incorrect for any chemical to be not labeled. But in this case, we do not label because just accidentally, I don't want you to know what it is. Now I can tell you, this is ferric chloride, FeCl3. No acid, no base. This is not a acid-base reaction. Okay. The reaction will come next. But you see, there are two colors that have been produced. Have you heard about Prussian blue? So the blue color that you see here is actually Prussian blue. How is it made? You might have read this chemistry, right? So, okay, so here's the chemistry. The one which made Prussian blue was painted with potassium ferrocyanide, whereas the one which turned blood red or maroon was painted with potassium thiocyanate. Remember, there is no cyanide here. Cyanide is toxic. So upon spraying with ferric chloride, one forms Prussian blue, one forms this complex, which has a blood red color. And you can do this in a more creative way. You can even think of 3 different colors. I have not done that, but if you know chemistry, you can think about doing it in a completely different way, generate the entire spectrum. Speaking of spectrum, we will roughly create the spectrum at the end. Yeah.
Why the words were not visible to us earlier?
Because they're all colorless. Colorless. Okay? Both thiocyanate and ferrocyanide are colorless. In fact, ferrocyanide turns slightly yellowish upon storage. Some of it becomes ferricyanide, which is a light yellow color. Okay, so that's why for the reverse side, okay, a little bit of yellow was visible. Okay, but we tried to hide it from you as much as possible. Okay, all right, yeah. In this experiment, yes, but as I said, in principle, your sky is the imagination. Okay, sky is your limit. You can think about any other chemistry to produce other colors, but I'm trying to do it in such a way that things are all safe, okay, and not using toxic materials here, okay? All right. Every household in the world, no matter how rich or how poor they are, typically have 3 chemically pure substances in their house. What are these? Salt is one. Vinegar, not everybody uses vinegar. Citric acid, huh? No. Water is correct. Water may be bacteriologically impure, but chemically it can be 99.9% pure. Third? No. Sugar. Somebody said sugar. Sugar. Okay, of course, detergent also one would have, but I'm talking about chemically pure substances. Detergent is not a pure substance. Okay, it's a mixture of many things. In fact, you'll be surprised to learn the chemistry of detergents. Now, what makes sugar different from the other two? Sugar is an organic compound, and it's also what is called an optically active compound. You have all studied optical activity, and you know that when there are mirror images, but they do not overlap, those molecules are called chiral or optically active substances, right? Sugar is a good example of that. Optically active substances have identical properties, completely identical properties, physical properties, boiling point, melting point, but in certain aspects they differ. One is the optical activity, because optical activity distinguishes the D versus L, the dextro versus the levo. They also are different in the sense how we perceive them through taste or smell. Sugar is optically active. If I take the mirror image of sugar, it will not taste sweet. Similarly, some molecules which are listed in the next slide, these are molecules, are you familiar with this sort of chemical structures? Plus 12, you should know. The one on the left comes from oranges. So those who make orange juice, the companies, they produce a tremendous amount of this molecule called limonene. Okay, but that is R-limonene that smells of orange. And that is often used as an organic solvent for many purposes. Whereas the S, the mirror image form, has a smell like turpentine. Very similar molecule called carvone. The R-carvone smells like mint, pudina, okay? Whereas the S-carvone smells like caraway seeds. Caraway seeds are like small cumin seeds, but these are used in high-quality biryanis. I'm sure that many of you like biryani, right? Or you don't. So if you go to a nice restaurant and ask for biryani, they will probably use this. This is also called shah jeera in Indian language. So that is similar, not identical to caraway seeds. So I am not going to do an experiment with this, but I have 4 samples of this because this is something that everybody reads in the books. And we tend to think that seeing is believing. But I think smelling is believing, right? So I have 4 samples of these. So during lunchtime or any time during today, you can come and take a look at it. Smell the limonene and then the other limonene, and you will experience the difference in the smell. Okay, periodic table and chemistry. What time is it actually? 1:34. Let me stop here. Okay? So then we will continue for another 40 minutes. Okay, let me pause it here so that we start from here. Okay? Yeah. Let's target 2, but 2 may be unrealistic. So 2:15. 2:15 is okay? Anyway, during lunch, we can also have discussion. I assume that we can also have lunch here? Yeah, okay, thank you. I will just blank this one.
So wait for lunch and come back by 2.
Because the most interesting experiments are waiting for us after lunch. Okay, I didn't want to do those before when you are still hungry. Okay, you are probably thinking about food. Yeah. You want to smell? Limonene samples are here. Here. This is carvone. These 2 are carvone. This is orange. And the other one is turpentine. Other one you have opened? And this is carvone. One second. Mint. Peppermint. And this is like the shah jeera. Okay, be careful. Don't spill it. So you guys will be able to manage everything here? Okay. Yeah. Yeah, keep it. That's the one. I know. But all brands, all this buttermilk brands have either, I mean, I chose this because this is the least amount of salt, 500 milligram of sodium, but many others which are available in Bangalore have 600 milligrams. So, as I said, in your age, it's okay to drink maybe 2, especially if you are doing some exercise and you are sweating, but I wouldn't take more than 1. Even after this, I usually prefer to now share with my wife, for example. Take only 100 ml. Okay. You want to smell? You can come back and smell. You know, don't smell it for too long because your receptors, nasal receptors will get saturated. Huh?
Like there is one pudina chips like that.
That is the carvone, our carvone. That smells like peppermint.
And the other one is
Orange.
Sajira.
Shajira. Shajira and caraway seeds are not exactly the same, but close. Okay, let's go have lunch. You can always smell it later. You give it to one of my students here. This is our carbon, mint. Pudina.
We're creating the way.
But what is important is to compare the two. This will not smell like biryani because biryani has a very complex flavor. Louis, you know biryani. This is rice cooked with meat.
Not necessarily meat.
Yeah, there is a vegetarian biryani also that Gaurav eats. I think this one needs to be refitted. I think this came off. Okay, let's go have a quick lunch and then we come back. Oh, actually, I have 80 minutes left. I've done only 40 minutes. I thought I have only 40 minutes. 40 minutes would not have been enough. Now, if any of you have any pressing experiment to do, feel free to take some time off because I may not need all 5 of you together after lunch. So if you have something that is going on and you want to spend some time there, come back, fine with me. Okay, that's up to you. Okay, let's go. And then I need to make sure that I don't take this thing with me. And I think I will. How do I stop this? All right. We already have seen periodic table, but little more, and I want to put a little twist on the periodic table. Okay? I'm going to show you a periodic table which you may not have seen before. This is available in this website, and it was launched by IUPAC. Have you heard about IUPAC? Okay, I'll say a few more things about IUPAC towards the end. Oh, my timer has to be turned back on. Okay, so this is called isotopesmatter.org, and it not only talks about elements in the periodic table, but also about their isotopes. Okay, because it brings into discussion why isotopes are important. Okay, so this is how the front page looks like. As you can see that this was partly commissioned through IUPAC, and it was officially released in 2016 in a place called Kuching. I'm also going to take a bit of geography test for you. Okay, where is Kuching? No? Okay, we'll come back to it at the end. Okay, let's move forward. For example, there are many examples where isotopes have been shown to be very useful. And one such example is about this mummy that was found in the Austrian Alps in the 1990s. Because, the glaciers are melting everywhere because of global warming, and then brings out things which were buried under the snow for many centuries sometimes. In this case, by analyzing very carefully the isotope composition of various parts of the body and the surrounding equipments, they were able to figure out where this guy, who was named Otzi, where Otzi lived, where he grew up, what he did, well, approximately, and so on and so forth. You might have heard about radiocarbon dating. Okay, but that is just one application of carbon-14. Okay, from this website, you can read a lot more about what isotopes can do. They are also extensively used by geochemists to find out more about soil, about the geology of the ground, about the past. For example, you often hear that, dinosaurs lived here some 60 million years ago. How do we know that? And some of these studies are done through isotope analysis. I won't go into the details of it. What is the most common isotope that you know of? Hydrogen. That's the most abundant element, right? Hydrogen and deuterium. So just like we have H2O, we also have D2O. D2O has another name. Heavy water. Heavy water. Why is it called heavy water? Why is it called heavy water? Molecular weight is more, but density is also more. This is the density, boiling point, melting point of D2O versus H2O. H2O everybody knows. All right. Have you ever seen D2O? No. If somebody offers you a glass of D2O, would you drink? No. Because nobody will offer you a glass of D2O. Very expensive. And then it will slow down the biological processes in your body. For example, here I have a tobacco plant grown in 0% D2O, that is 100% H2O, 30%, 50%, 60%, and 70% D2O. You can see that the growth has severely been retarded. Plant can still survive, but a small mouse can be killed by about 10 ml of D2O. Okay? So, because it slows down various processes in the body, if you read chemistry beyond BSc, you will know why that is so. This is called kinetic isotope effect. Yes?
Why tritium not called as heavy?
Okay, that is part of the reason is that tritium is radioactive. Okay, and therefore you can never have T2O. Tritium, or it is also sometimes called tritium. The third isotope of hydrogen, which has an atomic weight of 3, 1 proton, 2 neutrons, that is radioactive. Okay, and therefore you cannot have a pure substance such as T2O, you always have D2O mixed with, or H2O mixed with a small amount of HOT. HOT. It's hot because it's radioactive. So when somebody writes HOT, chemists think about hydrogen, oxygen, tritium. That has been used very extensively for many chemical studies, but getting a pure sample of T2O will require very special equipments. Of course, that will be heavier than D2.
Purpose of using tritium?
Because of the radioactivity. It is used as what is called a tracer. For example, I'll give you an example when I talk about Danube. Where is Danube? No, you don't get any prize. Okay, because I will keep asking geographical questions. But that's important. Okay, all right. Yeah. That means not in the soil, but using a separate, only water-based nutrients. Tobacco plants are resistant to many diseases, and they are more robust. We don't want them to be so robust, but they are, and that's why tobacco plants are grown. But for any other plant, the answer will be same, but some of them will probably die even with 50%. Okay, let's move forward. We will do an experiment with H2 and D2O. How does that sound? For example, I will give you, keep it frozen. I'll give you 3 milliliters of H2O and 3 milliliters of D2O. Which experiment would you do to prove that H2O is indeed heavier than, D2O is indeed heavier than H2O? There was a paper, the first person who made D2O for the first time, he actually did this. He tasted D2O and he said that eventually, he actually put it in the mouth and spat it out. Only 1 ml. And he said it tastes no different than H2O. Because nothing was known about its other activities.
But he knew it was a D2O.
He knew it was D2O. Because from density he would know. What experiment do you think can be done? Again, we will follow Occam's razor policy. We will do, in a twisted way, we'll do an experiment so that everybody gets to see. See, the simplest experiment is, I can weigh 3 ml of H2O, that will be 3 grams. I can weigh 3 ml of D2O, that will be 3.3 grams. But if I put a balance here and weigh, everybody will get bored because you are not seeing the display here. I want to do an experiment here so that everybody gets to see this. Now, let me ask you this question. 3 ml, how am I going to boil? And you have to be able to see, all of you have to be able to see. Why?
Then it would boil more easily.
You have to realize that I have only 3 ml, which is this little, less than a teaspoon. Let me then elaborate. H2O ice floats on H2O. D2O ice will also float on D2O. But what about D2O ice and H2O?
As an indicator density, we try to freeze both the solution and the one which is lower.
That's exactly what we did. This is my special design. One is H2O, one is D2O. Now my students never label these things because they said anyway you are going to do the experiment, you find out which one is H2O, which one is D2O. So actually I don't know which one is which. Colors are made from food colors. This is used in biryani, this is used in palak. If the palak is not fresh, sometimes you will find this. And in many food which, this, illegally they add, well, this is a legal green color, but this is actually a mixture of yellow and blue. Okay, all right. So let's try to do that. And this is ice salt. This is ice cold water. I need some more ice here. Thank you. And I will tell you why I'm using ice. And Nandita, I will also need you once I'm ready. I'm putting ice cold water in this measuring cylinder. Okay, so this is a way to do the experiment so that everybody gets to see. So I'll drop these two ice pieces. One will float, one hopefully will sink. And why ice cold water? That is because which has the lower melting point? H2O has 0 degrees, D2O is 3.8 degrees. Which one will melt faster? H2O. H2O has a lower melting point. So this water at 0 degrees is below the melting point of D2O, but equal to the melting point of H2O. So H2O ice will melt faster, hopefully. Let me get things going. I will come to that side, Nandita. These days they say go green. So let's go green first, all right? So hopefully it will either float or sink. I don't think that we have any other choice. Unless the density is identical to the water, then it will stay wherever we put it, right? And so this experiment is very simple. All you need to do is to have 3 ml of H2O or D2O and some food color, which you can buy for about 10 rupees. Nanita, you come and hold it like this. No, don't hold it at the bottom, so that we can, it's very humid in Bangalore for a change. Can you all see? You move back a little bit and bring it to the front. Bring it to the front. Stretch your hand. So everybody can get to see this. So I'm going to add this little piece of ice. Slow descent. Okay? Therefore, D2O. Okay? All right, hold it here now. Hold it at the top. Okay, and then the second part of the experiment is kind of boring. But this orange ice should float if it is H2O, unless you have blown up another sample of D2O. This amount of, thank you. This amount of D2O ice costs about 200 or 300 rupees. Each milliliter is about 100 rupees. And thankfully, this is supplied by Sigma Aldrich for this sort of demonstrations. But you can see that this fellow, broken, is floating. This has sunk. I'll keep it here. So, Simpa, you keep an eye on this, and when it is partially melted, you show it to others, because when it is partially melted, it will be liquid D2O at the bottom, and the remaining part of the ice will actually start floating on it. Because of the density difference, D2O and H2O will not mix that well, partly because it is cold. So the little piece of D2O ice will actually float on top. Why? Oh, this syringe is very easy to keep it and transport it. So when I travel to other places, they make these H2 and D2O samples, put 3 ml in the syringe, seals it with some wax or something, and then I carry it with me. And then I use this kulfi maker, which is a poor man's deep freezer, H2O and ice and salt to keep it frozen. See, we didn't have any we didn't bring any refrigerator here. So this was kept in ice salt mixture, right? You all are familiar with kulfi. I'm sure you like it also. So this kulfi process is ice and salt, and we keep it that way. Okay, that keeps a temperature of about minus 18 degrees. Okay, so this is a very simple way to detect H2O versus D2O. Okay, all right. What is the question here? Question I have already asked. What are the ways by which you can determine the difference between the two? Okay, I talked about elements in the smartphone. I'm digressing a little bit, but we are still in the periodic table. So smartphones contain a variety of elements in it, including many of the lanthanides. Okay, and largely the lanthanides are in the screen and in the electronics. Okay? And you can actually learn quite a bit as to what each of the elements is doing here. For example, in the casing, you have bromine and nickel and magnesium and carbon. What all are they doing there? Okay? Battery, of course, all of you know that this is a lithium battery, which has lithium, cobalt, carbon, aluminum, and oxygen. Okay? All right. But the main point I would like to present to you is that many of the elements used in mobile phones are getting depleted very, very rapidly. Not just the lanthanides, but many other elements. And unless we are careful, we'll run out of them. Yeah. Sodium battery is being developed, but lithium still wins in terms of its energy density because it has only an atomic weight is very, very low. So lithium battery can pack much more energy, much more efficiently than sodium. Sodium ion battery is being very actively researched on because sodium is so much cheaper, but lithium is still winning. Okay. We don't have lithium deposit in India. Yeah. How? Okay, that is a little more difficult to discuss here in detail, but basically batteries store energy in the form of chemical energy. Okay, and that chemical energy gets transformed into electrical energy during the discharge process. Okay, we will not talk about this, but we will show at the end how chemical energy can be converted not to electricity, but to another form of light, another form of energy. Okay, what is this elephant doing here? Any experiment that you have heard starting with elephant? Elephant toothpaste experiment, right. So that's the experiment we are going to do. How many of you have seen this? Oh, many of you have seen this. Okay, but not all. So it looks nice, but then as science students, as chemistry students, we need to know why you do this experiment. Okay. The experiment is basically the decomposition of hydrogen peroxide into water and oxygen. Hydrogen peroxide is what is called a thermodynamically unstable molecule. In other words, it has a high energy and it releases oxygen and becomes water and energy and becomes more stable. For example, anything that has a high potential energy will actually go to the lowest energy. Like on the floor, if I drop it, I won't. With the mobile phone. Okay, so this is a high energy state, that's a low energy state. So similarly, but then this process is very slow. And in principle, if I keep it like this, it can very slowly move and fall. But this is called a kinetically arrested state. Because the process by which it will fall is very, very slow. Process by which it breaks down is very, very slow. So normally hydrogen peroxide is reasonably stable. But then somebody was talking about catalysis in the morning. Okay, you can have certain catalysts that will speed up the decomposition. So this experiment is actually about catalysis. So we will use a catalyst which is sodium iodide. And do we have 100 ml? This was 100 ml. Okay, I think this will do. So to make the experiment a little fun, what we do is that we take liquid soap. Again, I don't promote any particular brand, so you can take any brand of liquid soap. Okay? And I will use what is called 30%, I'll use a little more soap maybe. Many of the experiments that I'm going to show you do not require exact quantities of the components. This is some other brand of liquid soap. Right? Hand wash. It says hand wash, this also says hand wash. We know the brands, they know the brands, but I may not. So I mix them together. and add hydrogen peroxide carefully, because this 30% hydrogen peroxide is not very safe. If you have to handle it, you should wear gloves because it will bleach the skin. In fact, many of these sort of skin whitening creams that are marketed, and they contain hydrogen peroxide. If I put a drop on my skin will turn white. So you know what happens in all these whitening liquids. And then I mix it with hydrogen peroxide, good amount of it. Okay, and very carefully wipe it and put it back. And just to be on the safe side, I will wipe my hands once more. This is not provided by all these, that is my own one. Okay, I just want to be careful about this. So this is a mixture of these two soaps and hydrogen peroxide. I put them together. Now here is a question. Oh, now I got it in my finger. This size. Water. No, it's okay. It's okay, I managed. Give me some more, one more. You'll see my fingers turning white in a few minutes. I was not very careful. Okay, all right. Now, if I add sodium iodide and it shows reaction, does it prove that iodide is the catalyst? It doesn't, because sodium can also be a catalyst. So what experiment shall I do to prove that iodide is the catalyst? Yes, I will add another salt. I can add common salt, but in this case I'm adding baking soda. What is baking soda? Sodium bicarbonate. Now you can see that the D2 ice is floating on its own melt. So I add this bicarbonate, nothing happens. What happens to the small beaker? Small one. Be careful, don't touch it because there might be something outside. And I need some distilled water here. So now I add sodium iodide, except I will dissolve it in water and then add. So with sodium iodide, nothing happened, right? We all agree. Sodium bicarbonate. If I make a mistake, please correct me. That will also help me make sure that I'm talking sense. Okay? Ready? Here comes the toothpaste. Okay. It's a little too liquidy, but I think it will foam up a little bit more. It's supposed to come out faster. It has become brown because some of the iodide got oxidized by hydrogen peroxide to molecular iodine. Okay?
But there are vapors from
That is steam. It's an exothermic reaction, exactly. So this reaction produces, whoa, I think we are in trouble. We need a bigger tray. So this has produced a lot of foam. Normally, if it is done in a smaller container, it will shoot up a little bit. Huh? Yeah, so now you see it is coming out. It's quite nice, and it's all oxygen bubble. Do we have the matchbox? And you can prove that it is oxygen because it's a post-combustion. Again, I'm not sure if I'm supposed to light up a match. Normally, if it is a liquid like this, you can see that it is glowing more. Okay, if it were carbon dioxide bubble, it will not glow, right? Okay, I think the size was fine. I think we contained everything into the correct dimension. All right. Of course. Okay. That is because I use about 30 ml of hydrogen peroxide and I use a very smaller quantity of sodium iodide, and that triggered the decomposition. And therefore, it is acting as a catalyst and not as a reactant. That little bit of color is not coming from all the iodide, but only a portion of the iodide. Good question. Yeah. Yes. It is used in sanitizers. In fact, that's another story. Some sanitizers use 0.125% of hydrogen peroxide. That is not for killing the virus, but to prevent formation of bacterial spores. In fact, one of my students has actually developed a method, and during the pandemic, we bought 5 of these brands which has hydrogen peroxide, found 2 of them had nothing. Okay, so that's another story. Okay, now, sorry? Why is it called elephant toothpaste? Because elephant needs a much bigger, quantity of toothpaste than what a small tube can provide. And that's only a way to entertain kids. If you show a picture and say elephant toothpaste, they all get excited. But then I had a little twist, because you are all 12th grade students, that this is actually an experiment on catalysis. Okay? All right. Yeah. Yeah.
I mean, you added the sodium bicarbonate in order to
Prove that it is not sodium ion.
Okay. So for iodine, there are other tests, right? Like starch. If you add starch, would it work?
No, why would it work? I'm not adding sodium bicarbonate to prove that iodide is needed. I'm adding sodium bicarbonate to prove that sodium is not a catalyst. So when I'm adding sodium iodide, it's not sodium, but it's iodide that is acting as the catalyst. Okay? Iodine, if I add iodine, nothing will happen. Potassium iodide will also work. Any iodide will work. Yeah.
When you define catalyst, it says that it doesn't get involved in the reaction.
That's right.
But here, iodine is
Small amount of it. Most of it is getting recycled. Small amount of it does get, so that's not on the catalytic pathway, that's a side reaction. So with many catalysts, you do get side reactions. Yeah. Sorry? I2 is different from I minus. Okay, just like sodium metal and sodium ion, which we have in salt, are very different. Have you seen sodium metal? Sodium metal added to water, what happens? Whoa, it explodes. Right, whereas sodium iodide, sodium chloride, we are eating every day. Right, so molecular iodine and iodide are completely different properties. That is because some of it has bleeded out of this thing. So some of the ferric chloride is now showing up upon drying, because I sprayed ferric chloride all over the place, right? And ferric ion eventually forms yellowish color because it is drying up now. If I spray only water, color will fade. Now, 1916 was a very important year in the history of chemistry, because chemical bonding was first put forward the way we know by G.N. Lewis. You are all familiar with Lewis dot structures? So Lewis wrote the first paper on chemical bonding in 1916. And that's why 2016 was declared as the international, not by United Nations, but by chemists, that it was 100 years of chemical bonding. You are familiar with these sort of pictures, right? Small orbital, big orbital, weak bond. Small hand, big hand, not a good handshake. Not a good handshake. So small atom, large atom, bonds are typically weak. I'm actually generalizing it. Don't take it 100%. For example, nitrogen chlorine, nitrogen iodine, bond strengths are pretty small. On the other hand, orbitals of equal size, firm handshake, strong bonds. We heard about Teflon in the morning. Very strong bonds, very hard to break. Okay, CC, CF, CO, these bonds are strong, single bonds. Now, weak bonds. Why do people make weak bonds? Because weak bonds carry a lot of energy. Like hydrogen peroxide, the OO bond is a weak bond, so that is energy rich. So those who make explosives, they will always look for a molecule which has many weak bonds. Now, one Ni bond is weak. If I have a molecule Ni3, that will be very, very energy rich. Imagine small nitrogen atom and 3 big iodine atoms surrounded by it. That's very, very energy rich. It is so energy rich that it would explode with very little provocation. You might have used these crackers where you throw it on the ground and they burst. Those are impact sensitive explosives. And see this one, I will show on a video because it's too dangerous to do this. Let me switch off this one. Yeah. Let's watch this video.
One detonation causes another to occur. One product of the reaction is violet iodide vapor.
So it produces nitrogen and iodine. Okay, and it is so shock sensitive. Yes?
Iodide vapor.
Iodine vapor. Iodine, that's a US accent. Okay? Iodine. Yeah. That's the next question. If it is so explosive, how do you keep it on the filter paper? That's question number 3. Okay? All right? Good question. So you get a special award. I hope Agastya Foundation will give some award to the students who are asking the most questions. I guess all of you should get this award. Weak bonds can generate energy. But I'll show you something even very weak. You have heard about hydrogen bonds? Now sometimes, the teachers need to tell you why we are studying certain subjects. Like, why do we study bonding? What's the point in writing all these, Lewis dot structures, and if you have a double bond or triple bond, life gets very complicated. Why bother about it? Because chemistry is all about making and breaking bonds. And chemistry is happening in our body all the time. We need to know that. Hydrogen bonds are very important in our body. What is it I am showing on the left? No. It's a protein structure, it's an alpha helix. DNA is on this side. But then I should also tell you, this is a DNA double helix, but this is not most of the common DNAs are. This is a left-handed helix. Most common, so therefore don't believe in internet 100% of the time. This is a left-handed helix, DNA double helix. It does occur in nature, but very rare. So hydrogen bonds hold the 2 strands together. Hydrogen bond keeps it in the helical form. I will say a little bit about alpha helix, about the discovery of alpha helix towards the end, if time allows. Hydrogen bond is also important for our life. In the absence of hydrogen bond, water would have been a gas and life would not exist. And it is because hydrogen bond in liquid water and ice are different that ice has a lower density than liquid water. I'll show you, try to show an animation here. You will see liquid water, water molecules are very compact, very tightly packed. But when it forms ice, it opens up and forms a structure like this. Okay? So let's see, this is liquid water, it's freezing and it's opening up. Okay, and this, you might have done experiments with, for example, a bottle of water, plastic bottle, you keep it in the deep freezer, what happens? It expands, the bottle gets distorted. If it is a glass bottle of a soft drink, it will break. We will take it to the extreme. We'll take an iron container, put water, and freeze it very, very rapidly by chilling it at minus 78 degrees. I mean, I'm not going to do it here. And you will see the reason. I'm going to show you only on the video.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightened. The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush wrapped. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is thrown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8-inch thick sides to burst.
So you can see that for making a bomb, you don't need RDX or TNT. But then there are some technical issues. If you want to freeze this volume of water, which will give you a good bomb, okay, it's not possible to freeze it so quickly, because as the ice forms on the inner surface, it also reduces the heat conduction. Ice is a better insulator than water. So it will not freeze together. So it will only pop off and not make a, yeah.
Let's say you increase the strength of the iron container a million times, and you freeze. Let's say it just can't explode.
Yeah.
There's not enough water frozen expanded volume. What happens to the water? Does it compress?
Yeah, it will be water under very high pressure. So the water structure can also change. People have in fact looked at ice at different pressures, and the ice structure gets more compressed because you're forcing it to give up some of the open space. So ice forms several sort of allotropes, I guess, upon very high pressure. So very good point that if you have, let's say, 1 inch thick vessel, that will not explode so easily. So ice will be under tremendous pressure, and I guess you can calculate the pressure, and then it will form a different phase of ice. If you look at the phase diagram of water under very high pressure, that will give you some idea about how it forms. Yeah. Yeah. Because in a solid, generally in a crystalline solid, things are always repetitive. So this is a structure, this is the so-called diamondoid structure. If you look at the structure of diamond, the carbon atoms occupy exactly the same hexagonal lattice. So in this case, each water molecule has 2 OH, they are hydrogen bonded to the oxygen of another one, and the 2 lone pairs on oxygen are also hydrogen bonded to 2 other OH groups. So this gives you a very regular structure where oxygen is tetrahedral. Tetrahedrally bonded, either 2 covalent bonds or 2 hydrogen bonds.
Why this forming so ordered?
Because in a crystal, that's one of the requirements, that in a crystalline solid you have an order. Like in sodium chloride structure, I don't know if you have studied that, or maybe you would study in class 12. There's a very interesting repetitive cubic pattern. And that's at the root of all crystalline solids, because that gives you a much lower energy, stabilization energy. Any other structure, you will not be able to write in a so periodic fashion. Crystal necessarily has to be periodic. Otherwise, it becomes an amorphous structure. Yeah. What is half filled? Yeah. Then in that case, the explosion will not happen, may not happen, because there is space for, because see, the problem is liquids are not compressible. So if it is half filled, the other half must be gas. Gases are much more easily compressed. And the volume expansion is actually not a very large percentage. So nothing will happen in most cases, even if you have 5% of the space vacant. Nothing will happen. There will be little bit of expansion of the water. The air inside will get slightly compressed, maybe from 1 atmosphere to 2 atmosphere. Okay, something like that. I'm just making a guess. No, it will not continuously expand, because ultimately the expansion of water is limited by this ice structure.
When we are placing it in that solution, it will only expand that much. Why not?
That's because it was completely filled and very.
If we fill our bottles completely, only it will distort.
It will distort, because there the bottle can expand, but the iron cannot expand. If you do the same thing with a glass container, it will break.
It will break, but it won't explode.
It will not explode, because there the freezing happens slowly. And here the freezing deliberately has been done very, very rapidly by chilling it to minus 78 degrees. The rapid cooling, because then you are freezing it in an instant. Even otherwise it will expand, but then the effect will not be so dramatic. It will eventually expand. But it will explode. It will explode, but you may have to wait for a little longer time. But don't do this experiment in the freezer of your, in the kitchen freezer, because next day you may not find the fridge. Okay, so we played with weak bonds, we played with hydrogen bonds. How about breaking strong bonds? Like C-double-bond-O bond. You know, this bond is very strong. The energy is given here. But then I will show you again on a video. You know, how many of you have seen dry ice? Many of you have seen dry ice. Why is it called dry ice? Solid state of carbon dioxide, then? It doesn't become liquid. It sublimes, right? Why does it sublime? Why carbon dioxide, solid carbon dioxide sublimes, whereas liquid, water ice does not sublime, melts? This has to do with something else which you may not have read, which is the principle is called phase rule. Because to make any solid melt to a liquid, the atmospheric pressure must be below a certain pressure called a triple point. Okay, for water, the triple point pressure is about 4.6 millimeter. So water will sublime, ice will sublime on the surface of moon, because there is no atmosphere. The pressure is very, very low. On the other hand, on the surface of Venus, carbon dioxide, solid carbon dioxide will melt to a liquid. For carbon dioxide, the triple point pressure is about 5 atmosphere. Okay, so if you have a vessel in which the pressure is increased to about 6 atmosphere, solid carbon dioxide will no longer be called dry ice. It will become liquid carbon dioxide. Okay. So we will react magnesium with dry ice and see what happens.
Magnesium is placed in a cabinet with a block of dry ice. The magnesium is ignited
Okay, you ignite it with a Bunsen burner and cover with another block of dry ice. Oh, she's just repeating after me. See, the burning magnesium. Yeah. There's no air inside.
Because of this reaction, carbon dioxide cannot be used to extinguish radiation.
If I have a magnesium fire, that fire extinguisher will be of no use. That's CO2 extinguisher, right? Or is it a dry powder? It's A type or C type? No, this will work because this is a dry powder extinguisher. CO2 extinguisher will not work if you have a metal fire, whether it is But you know, it's an amazing reaction. Magnesium burning in CO2 is essentially extracting the oxygen out of CO2 and reducing it back to carbon. You may say, does it solve our global warming problem? Can we take all the carbon dioxide, react with magnesium and convert it back to carbon? Answer is no, unfortunately, because magnesium does not occur free in nature. Magnesium comes from two ores, dolomite and magnesite. Both are magnesium source. So to make elemental magnesium, you have to put that much energy. That came out when we burnt it. Okay? So this is technically not possible, energetically not possible. Okay, we need to move forward. Can you break N and triple bond? That's even stronger than magnesium and carbon dioxide reaction. Because magnesium reacts, burning magnesium reacts with CO2. 2 Mg plus CO2 gives 2 MgO plus C. This is a thermodynamically favored reaction. And it so happens because magnesium oxide is a very stable molecule. That's why eventually it is thermodynamically or energetically it is favorable reaction. Yeah, you had a question?
Yeah, so the magnesium broke the strong bond.
That's right. Because MgO bond that is produced, that is even stronger than that. Okay? You need energy and a pathway and a catalyst. I'll answer it later. You have studied Haber's process? Okay. Now, the rest of the experiments will be all about colors. Okay? Because chemistry is not just black and white. Chemistry has a lot of colors. Okay? And something that, you know, I think I'm not wearing a very colorful dress, but those of you who are, or those of you who like colors, will appreciate that we have lots and lots of different colors. Here I talk about solvatochromism. You all have heard about polar solvents and non-polar solvents. So give an example of a polar solvent. Water. Non-polar? Benzene. We don't talk about benzene these days because we don't use benzene because benzene is carcinogenic. You say toluene. Toluene is a better example, okay, or hexane. There are certain compounds, colored compounds, which show very different colors depending upon the polarity of the solvent. Okay, and they are called solvatochromic. Very self-explanatory word, solvatochromic. And I will not do this experiment, but I'll simply show you this picture. It is, this particular molecule was made by a gentleman named Reichardt, a German chemist named Reichardt. It's called Reichardt's dye. And it shows, amazingly, different color with methyl, ethyl, and isopropyl alcohol. You see the difference in colors. And in acetone, anisole, and I'll show you one more impressive. You can come to my lab and actually see this, this one. This is kept in our lab. Dioxane, chloroform, acetone, and some of these things, methanol, ethanol, they have very different colors. Okay, so this molecule shows the largest color difference of any other compound. So this probably has a world record. Okay, so it's good to know that you can easily distinguish methyl and ethyl alcohol, because you know that in many places in India, people end up getting methanol poisoning. I won't describe how, but they do get killed because. Yes, yes. The dye has a deep green color in the solid state. You almost looks black. The last one is water. Water doesn't give any color because this is insoluble in water. Oh, whether there is anything underneath? Good question. You have to come to my lab and actually see this one. I think they have added something. It's not a fake experiment. Okay, so color changes with color changes with solvent polarity, and we will now see color changing with temperature. But before that, I need to have a drink of water. Is this water? No, I'll take some normal water. I don't know this. I will take the only from the bottled water. Not cold enough. I'll add some ice. I usually like things which are cold. Oh, something is happening. Is the water or the water is bad or the glass is bad? Water is bad or glass is bad? How do I prove that? No, by taking the water out, right? Water is colorless, empty. So the glass has a problem, but let's see what kind of problem. Okay? Color changes, right? Because the glass is built with a dye which is called a thermochromic dye. That becomes red below 10 degrees. So I don't use it for drinking, by the way. It can be safe if I don't use it for lab experiments. Okay, and then if it becomes below 10 degrees, it turns orange, but this is a reversible reaction. In other words, when I warm it with my fingers, which are hopefully at 37 degrees, it becomes colorless. Okay? And this is a glass I got from a publishing company. It says IISc 2011, International Year of Chemistry in 2011. And this was to celebrate 100 years of a very important event. And I'm focusing on this row only. What happened in 1911? It says IISc 2011. It doesn't say anything more. What happened in 1911? That should make you proud. No, C.V. Raman came much later. Marie Curie got the Nobel Prize. Marie Curie got the Chemistry Nobel Prize in 1911. So this was to celebrate her Chemistry Nobel in 2011. Okay? All right. I would like to move forward because we have a couple of more experiments waiting for us. And the next experiment will be, in fact, a simple one. This is something I don't want to do very seriously for this audience. This is largely meant for younger children. This Ag2AgI4, this is also a thermochromic substance. You know, in this glass, I do not know what material they have put in, some organic molecule, but the Ag2AgI4 is yellow in color. The corresponding copper salt is red in color. And this shows thermochromism at 50 degrees. This shows at about 70 degrees. This becomes orange. This becomes black. Okay, so children love it, and that's why I have painted a banana and an apple. So let's see what happens to the banana. Became orange. Gaurav, can you hold this? And this one only. This one requires a little more heating. Beautiful red apple gets rotten. But this is one of the examples in which the rotten apple becomes beautiful red again. I think if this happens in real life, that will be good news for the apple producers. And this has also come back to yellow color. Okay, this happens because of certain changes in the crystal structure, which are things that you will learn if you go past master's program. Yeah.
Both these were double source of silver iodine.
Double salt of mercury, iodine, and either silver or copper. With silver, you get the yellow color. With copper, you get the red color. Okay, what does this remind you? Okay, practical application is until a few years ago, the pizza delivery guys will have a little sticker which says hot. And then if it is not above 50 degrees, it will become black. I mean, that is one consumer application. But in many industries, chemical industries, where they have pipes transporting hot liquids, the temperature can be indicated by these thermochromic dyes. They can be painted with a color to indicate that this is hot.
One more question.
Yeah.
Is Lewis's original paper available?
Yeah. Yeah.
Just free copies of it?
Not free copies. From IISc we can get it because we have subscription. 1916 paper. Yeah.
The thermochemical dyes which you're talking about, is it a layer or
It is mixed with the plastic.
it can be
It is mixed with the plastic.
it can be formed like a layer, or it has to be made into a cup?
It can be. It's a powder. So even as a powder, it will show this thermochromic properties. You know, sometimes the spoons, plastic spoons, which are used for feeding children, some of them are available in the thermochromic variety because if the food is too hot, it will have one color. Okay, and when it comes to the feeding temperature, correct feeding temperature, it shows a different color. So that's another very important application. Okay, yeah. Yeah. And you can have different colors.
Does this change in color have anything to do with pressure?
No, in this case, it is not pressure, but it is change in the crystal structure with temperature.
Okay. No matter what the pressure is, it will change.
No, with pressure also certain molecules do change color. But, you know, that is a little difficult to achieve under normal conditions. Water bottle? Sure, why not? I mean, if it is cold versus hot, yes, you can use it. Yep. Yeah. Huh? Sorry?
It can be harmful to them.
Which one?
While using it in
Oh, in spoons? No. If they make baby feeding spoons, this has gone through many sort of quality control to make sure the dye does not leach out of the plastic. Okay, in a plastic, if you embed something, it will not leach out. Yeah.
Are these biodegradable?
Good question. I don't know. Some of the dyes may be biodegradable, but obviously the plastic is not. I'm using it for about 13 years now, day in and day out. And so far, a little bit of paint has come off, but otherwise the glass is still there. Okay, time 21 minutes. Okay, we need to move faster. Okay, next experiment based on this. It's more of a physics experiment. What does this picture remind you? Why is the sky blue and why is the setting sun red? All of you know that. Okay, so today we are going to do an experiment on that. The sky is blue because we see it only in scattered light. Why blue? Because shorter wavelengths scatter more than the longer wavelength. And the same thing happens when the sunlight comes through the dense atmosphere in the evening or in the morning. It passes through, it gets scattered, blue light gets scattered, and we see only the remaining part of it. Violet, our eyes are very less sensitive to violets. Yeah, violet and indigo we don't see as well as we see yellow, green, followed by blue. So I will show you with a laser that the laser is actually quite strong, but it's in the blue-violet range, and we don't see it very clearly. Yeah, but then most of the blue and the other shorter wavelengths are gone, so it is richer in red color. See, our eyes are also not like a spectrometer, that it will see all the frequencies separately. Yeah. Sorry?
When we see blue color in the sky, like in the afternoon, there are also frequencies of red color in it. So why can't
No, blue color we are seeing only the scattered light. Okay, because the blue gets scattered more than any other spectrum. Okay, so that's why it always appears blue. If you go to the moon, the sky will appear black because there is no scattering, no atmosphere, no scattering. Okay, let's. If there is nothing, if there is no scattering, there is no background light, so it will look black. No, not here. These are because of clouds. Can we pour this one out? I think the H2O and D2O, let us allow them to go back to nature. You know, D2O is actually made by, can you rinse it and have a little more water here? Okay, so we are going to see, you know, when light passes through a medium, what all can happen? Reflection, refraction, diffraction, interference, scattering, absorption. If there is absorption, again, many things can happen. Absorption can lead to absorption and loss of the energy as heat, absorption and emission of radiation, which is fluorescence. And the last example is absorption and chemical reaction. That is important for sustaining life, photosynthesis. Okay, so we will do a few simple experiments, water everywhere, in all of them. So, yeah, keep everything full. This you have seen perhaps. I have, what I will do, I will, yeah, so this is an example showing, so in terms of the fluorescence, you know, here is an example of fluorescence as measured in the 1850s, okay, by this gentleman named G.G. Stokes. So they did not have any equipment. So what he did was to keep solution of quinine. Remember, quinine was mentioned by Professor Natarajan? Malaria. We'll come back to quinine. But here is a quinine and sunlight passes through a blue window and it shows a blue fluorescence which is seen through a white wine glass. That acts as a filter here, that acts as a filter here. There is another interesting application of fluorescence. This is back to Danube. Okay, Danube is the longest river in Europe. Louis, you can correct me if I'm wrong. Okay, so this is Danube, and this long one, okay? And then this little one compared to that is the Rhine River. For some reasons, people believed that Danube and Rhine are connected. And the experiment that they did was to pour a fluorescent dye called fluorescein in Danube, and about 60 hours later, it appeared in a tributary, in a stream that connects to a tributary of Danube. So fluorescence has many applications because if you put it here, it is so sensitive that even after passing through the river, it appears through the underground channels and going to the other river, you can detect it. I said that I will talk about it as a tracer for tritium. You can do the same thing with tritium also. You can put some amount of tritium here, and if these are connected, you will find the tritium over there. Okay, so this is one of the interesting applications of fluorescence. Okay, this is just the description of that, but we are going to do some fluorescence experiment with quinine. All of you know this? Right. Many of you may not know this. This is called Indian tonic water, shown here. Okay, and since all of you are below 21 or 25, whatever the state law is, I've hidden that content of the other bottle. Now, why is it called Indian tonic water? When the British came here, the British had malaria, and the only medicine available at that time was quinine. So they started drinking water mixed with quinine and called it tonic water. And to make it more tasty, they added sugar, and they also added other things, which we need not be worried about. So this has nothing other than water, carbon dioxide, and sugar and quinine. Okay. Lights off, please. It was good for their health when mixed with appropriate other liquids. Okay, I'll pour some Sprite here. By the way, nobody drinks anything from this table, right? And I will pour some tonic water here. Oh yeah, that's how I could buy it. But it's not available in many smaller towns, so whenever I do the experiment in other places, my suitcase typically will have one extra. Maybe, I don't know. So there are two glasses, they look almost identical, right? One has, but the amount of quinine is very small here. One has Sprite, one has tonic water, but I know which one is which. I will turn my back and I will ask you to come and make it in some way that I don't see. Change the order or retain the order. I do not want to know which way it is. Done? Okay, thank you. So I don't know which one is which, but I have a blue laser. Okay, and that will show fluorescence from quinine. Lights off, please. One will show blue fluorescence, one will only show reflection. This is showing scattering, and this is showing beautiful blue fluorescence. Can you all see? Okay, so this obviously must be quinine containing water. That means the tonic water. That's a more difficult question to answer for your class. The question is, why does some molecule fluoresce? And that is because, okay, lights back please.
How is this fluorescence different from biological fluorescence?
Okay, we'll come back to that. And then you all know about refraction, and you can see this one. Okay, I'm actually pointing this way, right? And you can see the spot on the screen, right? Okay. In principle, I could show that with 3 different lasers, 3 different colors, I can get different refraction, which is the result, which is how a prism splits white light. Okay, I won't have time to do all that experiment. Basically what fluorescence is, I will come back to that when I show the last experiment, which is not very far. But I will also show some more example of fluorescence. This was quinine, okay? So this is the spectrum. And can I have the milk, please? Oh, that's milk. Okay, there are 4 measuring cylinders with water. I will add a couple of drops of milk. And then, a very important question. What's this? What's this? See, you are science students. You have to be accurate, brief, and clear.
Pink highlighter.
Exactly. This is a pink highlighter, this is a yellow highlighter. In science, there is no scope for making a generalized statement. You have to answer to the point, right? If this were an exam question, you will get a big 0. I put the pink highlighter here. This contains a rhodamine dye called solvent red 49. And this has a dye called fluorescein, the same dye that was used for looking at the connection between Danube and Rhine. Okay, now this is just plain water, and what to do? Because this will show only, transmission. That all of you know, that colorless liquid means it will transmit all colors of light. So I'll do a 4th experiment here. And here what I have, somebody gave me this vitamin B complex. I was having some throat infection. So I'll put this vitamin B complex powder here. Okay, vitamin B1, have you heard about the vitamins? Vitamin B, B1, B2, B6, thiamine. B1 is thiamine. B2 is? Okay, these are some B2. Okay, so I'll not tell you what it is, but I'll mix it. Okay. Okay. I don't have VIBGYOR, I don't have a spectrometer, but what I do have is a red laser. It was showing red until some time back. This is red, this is blue, and the other one must be green. Okay, so let's see what happens. With lights off, please. One of you have the torchlight, right? Keep the torchlight in hand just in case I can't see anything. Okay, no, there is enough background light. With red light, you see scattering. For some reason, the intensity is low, but do you see the scattering? Yeah, because that is milk. Okay, with the blue, it will be a little more easy to visualize. You see the scattering? And there is so much of scattering that the beam does not go and reach the bottom. And then let's try with the green one also. Again, green remains green, right? Second one, so let's keep this away. This was a pink highlighter. I put the red light. Again, you see a bit of scattering, right? I put the blue. It shows pinkish color, orangish. Now I put the green becomes yellow. You see here it is green, green, yellow. But the transmitted light is green. The transmitted light is green. Okay. You see that? That means that this yellow light green light has been absorbed by the rhodamine dye, and it is fluorescing in yellow. Okay. Now, with green we continue. Scattering. Okay, this is that medicine, B complex. That's not all. I now use the blue highlighter. Blue, pinkish, green. Blue becomes green. And here is vitamin B12. There also it becomes green. No, this looks green to me. Okay? So what has happened here is that, let's get the lights back again. So what has happened here is that fluorescein absorbs blue and gives you green fluorescence. Riboflavin, that is vitamin B2, that also absorbs blue light and gives you yellow fluorescence. Yellow, or I still think this is green.
Light green.
Okay, now let's do a little more fun. You have seen these color tables, RGB, red, green, and blue. If you mix them, what do you get? You know about complementary colors, right? RGB, if you mix them, you get white light. Okay. Now, one of them was our good friend quinine. So what we do, quinine gives blue and this gives yellow, and if I mix them, I should get white. Let's give that a try. I will trash the 7-Up. I will take some quinine. This is how chemistry is so much fun. I have quinine and then I mix it with a dye. One came from a can of tonic water. This came from a pink highlighter. And if I mix them and shine blue laser, I should see white light. Indeed, you see very close to white light. Lights off, please, once more. See, does it appear white? More or less white. A little bit of blue tinge. I can do different experiments. I can do a little bit of what is called titration. By adjusting the concentration of these two, I can get pure white light here. Incidentally, Louis in my group is trying to develop a white light emitter in the solid state, okay, using a different technology. Okay, and here you can see that blue is still blue. Okay, so you can see I get white in the top, whereas it becomes green when it passes through fluorescent solution. So again, by using very simple gadgets, except you have to be very careful while using laser pointers, because these are not good for your eyes. If you get hit by the laser, you may lose eyesight permanently. Okay, so I'm giving this as a warning so that you all are careful. Now, can you clear this place? So what we have seen here is green light becoming yellow and blue light becoming green. Okay? All right, coming back to nature. So this you have seen, all of you. Okay, they produce beautiful flashes of light. So this general term is called chemiluminescence, which is conversion of chemical energy into light energy without going through heat. Nowadays we have these LED lamps which work by electroluminescence. Conversion of, oh, I have only 1.5 minutes. Can I use 5 minutes more? Okay, maybe a bit more. Chemiluminescence uses chemical energy and converts it to light directly. Okay, so that is the experiment we are now going to do quickly. Thank you guys for your help. And I am going to, one more conical. I'm going to use, let me tell you the chemistry behind it. I am going to use hydrogen peroxide as my energy source. Okay, and react it with what is called oxalyl chloride. Okay, and what it will do is that it will produce this cyclic chemical structure which is it is sort of like two carbon dioxide molecules. You see a CO2 on the top, you see a CO2 on the bottom. It is as if two CO2 molecules have been stitched together. Okay. Now that's very unstable, and that breaks into two carbon dioxide molecules. And one of them I have colored black because that's normal CO2. The red one actually contains all the extra energy. Now, if I don't do anything, it will lose energy as heat. And that's very boring. The solution just gets warm. Big deal. But I'm going to use other fluorescent molecules, such as the ones we have seen before, and they will get electronically excited. So this, essentially the star means it is electronically excited. The electron in that molecule, one electron, is at a higher energy state. So in turn, there is a transfer of energy between CO2 and the A molecule. Now A is the electronically excited state. And when it comes back to the ground state, it emits a photon. Depending upon A, we can tune the color of the photon and get different lights. So that's what we are going to do today using 4 different dyes: diphenylanthracene, rubrene, perylene, and tetrazine. And they will show the color like this: orange, cyan, and green. Okay, so give me a few minutes to set things up. My team has already helped me, and I will use my very special micro spatula for this purpose. Are you okay? Am I taking too much time? Are you sure? You're fine? Okay, thank you. So I will put diphenylanthracene on the extreme left from your side. Then in the second one, I'll put rubrene. It's always important to label things, right? So here I put rubrene, and this is very expensive, okay? And again, I get this from Sigma Aldrich. And the third one, I will put perylene. Perylene is not very expensive. It is also used in certain, not as perylene, but some derivatives are used in car paints. Rubrene is used only for research purpose. Not all of them are very useful. The other one, last one, looks like 2 naphthalenes stitched together, but it's probably 100 times as expensive as naphthalene. 100 milligrams cost about 10,000 rupees. So this must be worth maybe 500 rupees worth. I don't know. And I will dissolve these in small amounts of dichloromethane. Some countries are banning the use of dichloromethane for certain purposes, but it is still not banned here, but we are using only small amounts and in a cold atmosphere, so it should be fine. I dissolve all of them in dichloromethane. As you can see that they are already showing some signs of fluorescence, right? And I need 2 droppers here. Okay. This is not a particularly nice chemical either, oxalyl chloride, but I'll keep everything handy so that I don't have to move anything. So I will do the left 2 first. I add oxalyl chloride here. Okay? Lights off, please. Complete dark, because we don't need light. We are going to create light. Okay, are we ready? Yes, sir. So, on your left, you will see bluish orange, bluish violet, blue violet, and on your right, you will see orange. Okay? As promised, you see blue, violet, and orange. And it turns out that these two are complementary colors. So if I mix them, what are we going to see? White light. Let's do a titration experiment here. It looks white. It starts with a bit of orange, then white, and the white will not last for too long because the orange is not very stable. It will become blue again. Okay? It is getting more towards white. You can see who is moving it around. It's bright enough. Let's keep it there. It will become eventually blue. And let's do the experiment with the remaining two. One will show a cyan, and the other one will show green color. The green will not last for too long. You see, this has become blue again. Okay? We can, in fact, do the titration once more. You see how the color changes. And this is real emission of light, right? It became white again, or close to white, and blue again. So the last two, this is my last experiment, but then I would like to play a couple of videos if time allows. Okay. And cyan and green. Let me stir these around a little bit. You see cyan from on your left with perylene, and blue from green from tetracene. So I can now arrange these things in roughly in the VIBGYOR. Okay, violet, indigo, blue, green, orange, red. Okay, so we have roughly created the VIBGYOR covering these 4 different dyes. Okay, so you saw an example of how chemical energy, and these are all cold. There's no heat evolved here. So chemical energy directly getting converted into light energy. So why does it happen? This happens because these molecules are extremely fluorescent molecules. So they don't lose the excitation energy in the form of heat. In order to understand these things more closely, you have to go to your master's level in chemistry, and then you will understand what is meant by photophysics. Okay, so that governs how some of these things happen. Yeah. Yeah, for example, green fluorescent protein, which was the subject of a Nobel Prize. These are also fluorescent molecules, but they show fluorescence. They are not chemiluminescent. They are fluorescent because when you hit it with a light, it shows emission of a light of a longer wavelength. That is a typical definition of fluorescence. Because fluorescence is a process by which you lose energy. Because you get excited, electronically excited, and when the excited molecule loses that energy, it comes out in the form of light. But why it is of a shorter wavelength, the lower energy, that will require some understanding of photophysics. Okay, let me... No, it will not. It will stay for 2 conditions. One is that the molecule is stable in the presence of all these reagents. The other one is that you continuously supply the fuel. Okay, but in this case, these are all very, very unstable molecules, particularly, perylene will stay for a long time. This, in fact, even when we go back to the lab, the color will stay. But diphenyl is also little visible still now. But the other two, rubrene and tetracene, they're more or less reacted under the conditions. So they're all gone. I still have another 5 minutes. Can I take? Is it okay? All right. This tower. I talked about breaking nitrogen-nitrogen triple bond. And somebody said something. Haber's process. This, in fact, was one of the reactors Haber and Bosch designed, and this was used for 55 years and produced close to 1 million tons of ammonia. And as you know, ammonia is used as a fertilizer, and that keeps us alive, right? And this is kept as a monument outside the BASF factory in a place called Ludwigshafen in Germany. Okay, let's see what else do I have. This is a gentleman who got 2 unshared Nobel Prizes. One in chemistry, one in peace. Name the scientist. Students only. No options. There's only one person like him, so there is no option. Linus Pauling. If I zoom the books behind. No, it's a pixelated, it's not a high resolution picture. I took this picture, in fact, when it came in a newspaper, his interview, when I was a postdoc in Berkeley. At that time, it came in the newspaper called San Francisco Chronicle on a Sunday. So from that, I have saved this picture. I actually saved the newspaper, and then when technology became available, I took a picture and saved it. Okay, I have a video, but I'm not going to show you because this is another 7.5 minutes, and we are already... You want to see? Okay. Quickly, I will then do a bit of fast forward, but the reason I want to play this is because Linus Pauling was trying to find the structure of proteins for a very long time. For 11 years, he was not successful. And finally, he will talk about it in this video. He was in Oxford in a hospital bed because he was suffering from flu. And he had nothing. He got bored reading detective stories. So he took a piece of paper and started folding it. He took a piece of paper, drew the chemical structure of a peptide and started folding it. And by folding, he came up with the alpha helical structure. Actually, we didn't do one experiment, okay? But that's okay. I deliberately did not display the slide because time was kind of taking, time was a little tight. So he talks about how he discovered this alpha helix. Okay, so I'll play this part of the video only. Let me make sure that it works. 1 second. No, there is some problem, so I'll play it from the file. Oh, this got de-linked from my app. Okay.
I like to understand the world. I like to think about new ideas. I like to think about problems, again, different ways of finally getting an answer to.
Linus Pauling was convinced that understanding structure was the key to unlocking some of the mysteries of the universe.
To understand the human body, we must know its structure in terms of the cells that make it up. If we want to understand cells, we must know their structure in terms of molecules. If we want to understand molecules, we must know their structure in terms of atoms.
Let me move forward.
Where he was to remain for more than 40 years, every science and math class offered. He went on to study and then to join the faculty at the California Institute of Technology in Pasadena, California, where he was to remain for more than 40 years. After his 1925 graduation from Caltech, While he studied with European physicists who were developing the new theories, bored with detective and science fiction stories, he began to ponder the structure of proteins.
I took a sheet of paper and sketched the atoms with the bonds between them, and then folded the paper to bend one bond at the right angle, so I wanted to develop it to the other, and kept doing this, making the helix until I could form hydrogen bonds between one third of the helix and the next third of the helix. And it only took a few hours of doing that to discover the alpha helix.
The alpha helix was
Okay, so in the interest of time, I am cutting it short, but you can probably view it on YouTube. I would like to move forward and finish in the next 2-3 minutes. This is what Pauling's that message essentially tells you, that he did not succeed for 11 years and still he did not give up. Okay, looking at the structure of alpha helix. This was also mentioned that in the morning, that keep your eyes open. So that's what I would like to recommend to you also, except when you go to sleep. The other point is Pasteur's name also came in the morning, Louis Pasteur's name, and he made a very profound statement: chance favors the prepared mind. You know, you might find nature with challenging problems presenting to you, but if your mind is not ready, you will not be able to explore or exploit that. Somebody else will do it. So keep your eyes open and look at things around you. Here's a bonus question. What does this remind you? This is a kind of a PJ, but nevertheless. What do you see on the bottom? And what do you see on the top? Carbon with 3 hydrogens. What is it called? So it is methyl orange. I thought, let me provide a bit of entertainment at the long hours. I mentioned about IUPAC. You know, this is IUPAC president last year. He is no longer the president, Javier Martinez. And this was an event we did in Cape Town. So I'll do a little bit of advertisement now. This is a program in National College in Bangalore with people from the neighborhood. And there was one in Kuching. Kuching is in Malaysia, right? Kuching, and here is another one in Malaysia last year, and one in, you know where this is, Kolkata, and there are a couple more here, but then this space is reserved for today's program. All right, so I'll put pictures here from this event if we manage to get a few more. And as I said, chemistry is everywhere. So I would also like to take this chemistry to other places. For example, someday I would like to do it here, and I'm looking for audience. I already have a boarding pass. This is July 2026. So if you want to see this show again and the next version, 2026 version, you book a ticket through NASA and we will meet at Mars. Okay, all right. Elephant comes back because of something called a periodic table song. How many of you have heard this? Okay, this was a song created by a mathematics professor named Tom Lehrer. He was a professor in Harvard in the 1950s, and he created a song based on the elements known at that time. I have two versions, one with animation and one song is sung by Tom Lehrer in 1967. Which one would you like to hear? Not both, because we are really running out of time. And somebody will kill me if I don't show up at 4 o'clock. Okay, so animation. And you can sing, you can dance to the tune. There's no order here.
What kind of order should it?
I thought that it was alphabetical for David.
No, they weren't. So there must be some order for it to be.
This is the one I will play just for a minute or two. You will see how Tom Lehrer look like. Okay, I'm sorry, I had to kill it, but you will find this on the internet. So with this, I would like to thank again my team members, Dr. Palani, and all of you for your patient hearing. Thank you very much. This is the end of my presentation, but this is not the end. If any of you would like to get in touch with me or any of my team members, please do not hesitate. If you have any questions, I'm actually working on an IUPAC project to take chemistry beyond the boundaries of any country. And we will probably have every month 1 hour of online interaction with students at different age groups. And so this will be a global experiment, but we will start with a small Indian trial run. And I will be in touch with Agastya Foundation and JNV team to reach out to some of you and perhaps to some of your younger friends. That is one thing. Secondly, another point that came up in the discussion in the morning is that many of you felt that there are not, that you read a lot, but then you don't do enough experiments. This NCERT is actually completely changing the syllabus of class 6 to class 12. Class 6 book has just been completed, and many of these books are designed in a way that, as the NEP kind of suggested, to have a lot of activities. And class 6 book has been completed, and the other books will come up. I mean, this is too late for you guys, but eventually you will find textbooks for school children, NCERT textbooks, which will be much more easy to read and more fun in terms of the activities that will connect basically the science with the real life science, with science that we every day use in our daily lives. So with this, I conclude, and if you have any questions, I'll be more than happy to discuss.
Any questions? Like the bioluminescence, does it work on, like, the background of bioluminescence is chemistry?
It is chemistry, except that the electronically excited species is generated in a biological system, largely through enzymatic processes. Same thing that happens, there's an enzyme called luciferase that is implicated, or that is basically active in the fireflies. So in fact, firefly luciferase is also an enzyme that is used very extensively in certain chemiluminescence studies.
I've seen a petri dish picture, sir.
Yeah.
It is like single fluorescence has been used there.
Yeah.
But different parts of the petri dish was of different colors.
Yeah.
So does this fluorescence change the color based on the interaction with different types of proteins?
Yeah, it depends. See, ultimately, it is a chromophore or a small organic fragment present in an enzyme that is responsible for the emission. That is the chromophore, that is the light absorbing part. Much of the protein, in the protein structures, typically there are 3 aromatic amino acids, tyrosine, tryptophan, and phenylalanine. These 3 show absorption of light. Tryptophan shows fluorescence, but that is in the UV range, 340 nanometer. So there is a separate functional group in the fluorescent proteins. So sometimes depending upon the environment, the color can change.
Thank you, sir.
I have a question.
Yeah.
Like those hot wheel cars that came out there, when they were dipped in water, the color changed.
Which one?
Hot wheel cars, that small ones.
I am not. Cars, toy cars. I don't think I have seen those. In water, okay. It may not be thermochromism, it may be just a solvent polarity. Because once it is present in air versus water, and that polarity difference is very large. I mean, air is very nonpolar. And also that's largely solid, so you see the solid surface. But in water, it may show different colors. Sometimes it can also be a little bit different because of texture, because in many cases what happens, for example, many of these butterfly wings, they show light of different colors depending upon the angle at which you are viewing it. That is because of the sort of nanostructure on the surface. But that's a different phenomenon. That has nothing to do with fluorescence. Yeah.
What are the applications of D2O?
D2O is used very extensively in nuclear reactors and in science also. For example, in scientific experiments, for example, to find out how a reaction proceeds, reaction mechanism, D2O or deuterium labeling is very frequently used. And the other application is that in certain drugs, okay, it's very new. The first drug came out in the market in 2017, which has a deuterium in it. And what it does is that in certain drugs, the research is the following. Presence of deuterium will make the drug last for a longer time. Okay, because it reduces the degradation of the drug, because that process becomes slower. So by carefully replacing a hydrogen by a deuterium, sometimes you can make a drug more effective. And that's a very active area of research in drug design. Okay? Yeah?
Can we use calcium as catalyst?
No. Unfortunately, many people have tried finding catalysts for the ammonia reaction. And the one which Haber and Bosch developed, it's an iron molybdenum catalyst. Nobody so far has found anything better than that. Although some bacteria do it.
These fluorescence and EV is there inside EV.
Sorry?
Cathode is there inside EV.
That
fluorescence is same also.
That is a little bit different because there you are using an electron beam to induce what is called a phosphorescence. Okay, that's a slightly different technique. There also lanthanide elements are used in the solid. I mean, that TV of course is gone now. The electron gun type, old CRT type TVs.
Any other questions? I would like to thank Professor Udaya for making the session really fun by experimenting so many things, and we learned a lot. So we have a okay for you, sir. I would like to Yogalakshmi to hand it over to you.
Thank you very much. Let me. Thank you. Thank you very much. Okay, so I should not run away with these microphones. So this is yours and this goes back to them. So thank you all and enjoy your stay in Bangalore in IISc. And feel free to visit my lab. Thank you. And be careful while doing this. You will be treated with reward. Yeah, who can do it? But I have somebody waiting for us.